हेलो दोस्तों, आज हम फिजिक्स क्लास 12 का पार्ट 2 मैराथन स्टार्ट कर रहे हैं। इसमें हम चैप्टर 8 से लेकर चैप्टर 14 तक कंप्लीट कवर करेंगे। और हाँ, अगर आपने पार्ट 1 चैप्टर 1 से 7 अभी तक नहीं देखा है तो टेंशन मत लो, मेन प्लेलिस्ट का लिंक डिस्क्रिप्शन में डाल दूंगा। वहां से आप इजीली पार्ट 1 के लेक्चर्स देख सकते हो। इससे पहले मैंने आपको बता दिया था, जूलॉजी और बॉटनी क्लास 11th प्लस 12th कंप्लीट करवा चुका हूं, फिजिक्स क्लास 11th भी पूरा हो चुका है और अब फिजिक्स क्लास 12th दोनों पार्ट्स के मैराथन अवेलेबल हो रहे हैं। सब्जेक्ट के आईपैड हैंड रिटन नोट्स सिर्फ 95 रुपये में मिलते हैं। नंबर डिस्क्रिप्शन में दिया है, आप कांटेक्ट करके डिटेल्स ले सकते हो। बस एक रिक्वेस्ट है, प्लीज इस वीडियो का टाइम स्टैम्प कॉमेंट सेक्शन में लिख देना ताकि और स्टूडेंट्स की हेल्प हो जाए। और जितनी भी मैराथन वीडियोस हैं उनके टाइम स्टैम्प्स भी कमेंट में डलोगे तो सबको बेनिफिट मिलेगा। तो चलो कमल के मैराथन को शुरू करते हैं, फिजिक्स पार्ट 2 की मैराथन को। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी मैक्सवेल्स इक्वेशंस और डिस्प्लेसमेंट करंट जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम के अलग अलग वेव्स को याद करते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त, इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इंपॉर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Tanuj, what are you watching? I'm watching Wild Safari on the Discovery Channel. Nice. It is quite interesting and knowledgeable program. Aditya, would you please step aside? My remote is not working. Is it working now? Yeah, thanks. But why it happened? When you came in front of remote, it didn't work. Do you know that infrared rays do not pass through the body? Infrared rays? What are these? When we press the TV remote's button, it emits an infrared wave to the television sensor. When an object comes in front of the remote, then wave doesn't penetrate that object. That's why remote does not work if any object comes in its path. But how is it possible in case of radio signals which travel very large distances? There are many types of waves having their different respective properties. Remote control works on the infrared rays and radio broadcasting works on radio waves. Infrared rays have higher frequency than radio waves. And you know that the waves which have higher frequencies, their penetration power will be lower. Okay, I got my answer. It's really interesting to know about that fact and I want to know more about this. Students, today we will study more about the electromagnetic waves. Objectives. At the end of this lesson, you'll be able to define displacement current, know Maxwell's equation, define electromagnetic waves, explain Hertz's experiment, describe nature of electromagnetic waves, analyze electromagnetic spectrum. Displacement current. The current which flows through some part of an electrical circuit due to change of electrical flux with time is called displacement current. Consider a capacitor getting charged keeping the current I constant. According to Ampere's law, the line integral of B around the curve C must be equal to mu naught times the current I passing through a surface bounded by C. This means for the surface S1, closed integral of B dot dl is equal to mu naught I. But for the surface S2 through which no current flows, closed integral of B dot dl is equal to 0. It means there is an inconsistency. There must be a current associated with the changing electric field in the non-conductor between the capacitor plates. The rate of change of charge on the plates is given by epsilon naught d upon dt of EA, which is equal to epsilon naught d phi E by dt. Hence, the displacement current is given by ID is equal to epsilon naught d phi E by dt. The displacement current through the surface S2 has the same magnitude as that of the conduction current through the surface S1. Now, Ampere's law becomes closed integral of B dot dl is equal to mu naught multiplied by I plus epsilon naught d phi E by dt. Maxwell's equation. The following four equations, called the Maxwell's equations, are the fundamental equations in electromagnetism. Gauss' law for electricity. Closed integral of E dot dA is equal to Q by epsilon naught. Gauss' law for magnetism. Closed integral of B dot dA is equal to 0. Faraday law. Closed integral of E dot dl is equal to minus d upon dt of phi b. Ampere-Maxwell law. Closed integral of B dot dl is equal to mu naught IC plus mu naught epsilon naught d upon dt of phi e. Electromagnetic waves. Electromagnetic wave is the disturbance produced in space due to variation in electric and magnetic field vectors at right angle to each other and also at right angle to the direction of propagation. These waves are transverse in nature. The velocity of these waves in free space is equal to the velocity of light, which is equal to 3 into 10 raised to the power 8 meter per second. The electromagnetic wave are produced by an accelerated or decelerated charge of LC circuit. The frequency of EM waves is given by 1 upon 2 pi under root LC. Example. Let's take an example of electromagnetic waves. In a plane electromagnetic wave, the electric field oscillates sinusoidally with a frequency of 2 into 10 raised to the power 10 Hz and amplitude 48 volt per meter. What is the wavelength of the wave? What is the amplitude of oscillating magnetic field? Show that average energy density of electric field equals the average energy density of magnetic field. Let's see the solution. Given values are nu, which is equal to 2 into 10 raised to the power 10 Hz, E naught equals 48 volt per meter. We know that lambda is equal to C upon nu. By putting and calculating the values, we get wavelength of the wave, which is equal to 1.5 into 10 raised to the power minus 2 meter. We know that B naught is equal to E naught upon C. By putting and calculating the values, we get amplitude of the magnetic field, which is equal to 1.6 into 10 raised to the power minus 7 Tesla. Energy density of electric field is given by half epsilon naught E square. Energy density of magnetic field is given by half mu naught B square. We know that E is equal to CB and C is equal to 1 upon under root mu naught epsilon naught. On solving the above two equations, we get average energy density of electric field equals the average energy density of magnetic field. Hertz experiment. Hertz experiment. An induction coil is connected to two large metal spheres with a narrow gap between them to form a capacitor. Electrical oscillations are excited in the circuit by sending short voltage pulses via the induction coil to the spheres, charging one sphere positive and the other negative. In this ionized state, the electrons and ions in the air gap oscillate back and forth with the same frequency nu as that of the circuit. This process results in the production of electromagnetic waves of frequency nu. This circuit is called a transmitter because it produces electromagnetic waves. The receiver circuit consisted of a single loop of wire connected to two spheres, has its own effective inductance, capacitance and natural frequency of oscillation. Observations. When the resonant frequency of the receiver was matched to the transmitter, there is an energy transfer from the transmitter to the receiver in the form of sparks in air gap. The energy transferred was carried in the form of electromagnetic waves. When the gap in the receiver is perpendicular to the gap in the transmitter, no spark appears at the receiver gap. That is, no electromagnetic wave is detected. When the two gaps are parallel, the production of sparks in the receiver gap is maximum. Nature of electromagnetic waves. Electromagnetic waves are neutral, so they are not deflected by electric and magnetic fields. The electromagnetic waves show properties of reflection, refraction, interference, diffraction, and polarization. In electromagnetic wave, the electric and magnetic fields are always in the same phase. The electric vector of electromagnetic wave is responsible for optical effect and is also called the light vector. In an electromagnetic wave, the energy is propagated by means of electric and magnetic field vectors in the direction of propagation of wave. In an electromagnetic wave, the average values of electric energy density and magnetic energy densities are equal. The speed of electromagnetic waves in a material medium is given by the relation nu is equal to c upon n. Electromagnetic spectrum. The classification of EM waves according to frequency is the electromagnetic spectrum. There is no sharp division between one kind of wave and the next. The classification is based on how the waves are produced or detected. Let us describe these different types of electromagnetic waves in order of decreasing wavelengths. Radio waves. Lower frequency radio waves are generally produced by charges accelerating through conducting wires using electric oscillator circuits. They are used in radio and television communication systems. They are generally in the frequency range from 500 kHz to about 1000 MHz. Cellular phones utilize radio waves to transmit voice communication in the ultra-high frequency band. Microwaves. Microwaves with frequencies 3 GHz to 300 GHz range are produced by special vacuum tubes like klystrons, magnetrons, and gun diodes. Due to their high frequency or short wavelengths, they are suitable for the radar systems used in defense and aircraft navigation. Microwave ovens are domestic application of microwaves. Infrared waves. This covers wavelengths from 10 raised to the power minus 3 meter down to 7.8 into 10 raised to the power minus 7 meter. These waves are produced by molecules and hot bodies and are sometimes referred to as heat waves. They have many applications in industry, medicine, astronomy, etc. Infrared radiation also plays an important role in greenhouse effect. Infrared detectors are used in Earth satellites, both for military purposes and to observe growth of crops. Infrared waves are widely used in the remote switches in the household. visible rays. This is a narrow band formed by the wavelengths to which our retina is sensitive. It ranges from about 4 into 10 raised to the power 14 Hz to about 7 into 10 raised to the power 14 Hz. Light is produced by atoms and molecules as a result of internal adjustment in the motion of their components, principally that of electrons. The different sensations that light produces on the eye, called colors, depend upon the frequency or the wavelength of the electromagnetic waves. Different animals are sensitive to different range of wavelengths. Ultraviolet rays. This region covers from 400 nanometer down to 0.6 nanometer nearly. These waves are produced by atoms and molecules in electrical discharges. The sun is a very powerful source of ultraviolet radiation, and it is this factor which is mainly responsible for suntans, but most of it is absorbed in the ozone layer. UV light in large quantities has harmful effects on humans. Welders wear special glass goggles to protect their eyes from large amount of UV produced by welding arcs. UV rays are used in eye surgery, and UV lamps are used to kill germs in water purifiers. X-rays. X-rays having wavelengths from about 10 nanometer to 10 raised to the power minus 4 nanometer. X-rays can be generated by bombarding a metal target by high-energy electrons. X-rays produce profound effects on the atoms and molecules of the substances through which they propagate, such as dissociation or ionization. X-rays are used in medical applications such as diagnostic tool in medicine and as a treatment for certain forms of cancer. Gamma rays. These electromagnetic waves are of nuclear origin. Gamma rays lie in the upper frequency range of the electromagnetic spectrum and have wavelengths from about 10 raised to the power minus 10 meter to less than 10 raised to the power minus 14 meter. Gamma rays produced by many radioactive substances and are present in large quantities in nuclear reactors. These radiations are also emitted by radioactive nuclei. They are used in medicine to destroy cancer cells. Did you know? Maxwell was the first to understand fully the connections between time-varying electric and magnetic fields and to propose a set of equations for these. He showed that light is an electromagnetic wave. He developed a quantitative theory of color vision. Long waves are lower in energy than short waves. Long waves from space penetrate the Earth's atmosphere easily. The ionosphere, between 45 and 250 miles above the Earth, can reflect radio waves. Interference can affect the quality of the received radio signal, making it sound crackly or appear snowy or even show ghosts on a television picture. Summary. Let us summarize what we have learned. The current which flows through some part of an electrical circuit due to change of electrical flux with time is called displacement current. EM wave is the disturbance produced in space due to variation in electric and magnetic field vectors at right angle to each other and also at right angle to the direction of propagation. The electromagnetic waves show properties of reflection, refraction, interference, diffraction and polarization. In electromagnetic wave, the average values of electric energy density and magnetic energy densities are equal. The classification of electromagnetic waves according to frequency is known as the electromagnetic spectrum. Radio waves are produced by the accelerated motion of charges in conducting wires. Visible light emitted or reflected from objects around us provides us information about the world. Our eyes are sensitive to this range of wavelengths. Gamma rays are produced in nuclear reactions and are also emitted by radioactive nuclei.
तो मेरे प्यारे दोस्तों, ये था इलेक्ट्रोमैग्नेटिक वेव्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी मिरर और लेंस के फॉर्मूलास में कंफ्यूजन होती है? क्या जब तुम रिफ्रैक्शन और टोटल इंटरनल रिफ्लेक्शन के कॉन्सेप्ट्स देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम रे ऑप्टिक्स के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Hey kids, today we learn ray optics and optical instruments. You must hear that in desert one must have a misleading appearance of water at a certain distance. So now the question arises that why it happens. The answer is that the illusion of water is due to total internal reflection. It is optical phenomenon that creates illusion of water with inverted images of distant objects. So, throughout this module we learn reflection and refraction of light. Objectives. At the end of this lesson, you will be able to explain reflection of light by spherical mirrors, state laws of refraction, understand apparent depth, explain total internal reflection, discuss applications of total internal reflection. Reflection of light by spherical mirrors. Reflection. The angle between the incident ray and the normal to the reflecting surface is called the angle of incidence. The angle between the reflected ray and the normal to the reflecting surface is called the angle of reflection. Laws of reflection. The angle of incidence is equal to the angle of reflection. The incident ray, the reflected ray and the normal to the surface lie in the same plane. These laws hold at each point on any reflecting surface, whether plane or curved. Spherical mirrors. A mirror formed from part of a spherical surface is called a spherical mirror. There are two types of spherical mirrors: concave mirror, convex mirror. The spherical mirror, in which light is reflected from its inner concave surface, is called a concave mirror. The spherical mirror in which the light is reflected from its outer convex surface is called a convex mirror. The spherical mirror has a radius of curvature r and its center of curvature is located at point C. The geometric center P of a spherical mirror is called the pole. The line joining the pole and the center of curvature of a spherical mirror is called the principal axis. Sign convention. The distances measured in the direction of incident ray are taken to be positive and those measured opposite are taken to be negative. The heights measured upwards are taken to be positive and those measured downwards are taken to be negative. Focal length of spherical mirrors. Rays that travel close to the principal axis of a spherical mirror and make small angles with it are called para-axial rays. The point F is called the principal focus of the mirror. The distance FP between the pole and the focus is called the focal length of the spherical mirror, denoted by F. Relationship between focal length and radius of curvature. F is equal to R by 2. Images formed by a concave mirror. When the object is beyond C, the images A. Between C and F, B. Real and inverted, C. Smaller than the object. When the object is at C, the images A. At C, B. Real and inverted, C. Same in height as the object. Images formed by a concave mirror. When the object is between F and C, the images beyond C, real and inverted, larger than the object. When the object is between F and P, the images behind the mirror, virtual and erect, larger than the object. The mirror equation. The given figure shows an object AB and its image A', B' formed by a concave mirror of focal length F. For paraxial rays, MP can be taken as a straight line perpendicular to CP. Then the two right-angle triangles A', B', F and MPF are similar, so that A', B' by MP is equal to B' F by FP is equal to B' P minus FP by FP. Since MP is equal to AB, we can write A' B' by AB is equal to B' P minus FP by FP. Name it as 1. Since angle APB is equal to angle A' PB', the right-angle triangles ABP and A' B' are also similar, so that A' B' by AB is equal to B' P by BP. Name it as 2. Comparing equations 1 and 2, we obtain B' P minus FP by FP is equal to B' P by BP. Name it as 3. On applying the sign convention, we get object distance BP is equal to minus U. Image distance B' P is equal to minus V. Focal length FP is equal to minus F. So, equation 3 can be reduced to minus V minus of minus F by minus F is equal to minus V by minus U, or 1 by V plus 1 by U is equal to 1 by F. This relation is known as the mirror equation. Linear magnification M. The ratio of the height of the image H' to the height of the object H, M is equal to H' by H. For the given figure, linear magnification is minus V by U. Example. An object is placed in front of a concave mirror of focal length 10 centimeters. What should be the position of the object so that its image is at a distance 20 centimeters in front of the mirror? Solution. Given F is equal to minus 10 centimeters, V is equal to minus 20 centimeters. 1 by V plus 1 by U is equal to 1 by F. 1 by U is equal to 1 by F minus 1 by V. 1 by U is equal to 1 by minus 10 minus 1 by minus 20. It implies 1 by U is equal to minus 1 by 10 plus 1 by 20. 1 by U is equal to minus 2 plus 1 by 20. U is equal to minus 20 centimeters. That is, object should be at a distance 20 centimeters in front of the mirror. Refraction. When a beam of light encounters another transparent medium, a part of light gets reflected back into the first medium, while the rest enters the other. The phenomenon of the change in direction of a beam of light in one medium when it enters a second medium obliquely is called refraction. The angle r between the refracted ray and the normal to the refracting surface is called the angle of refraction. Laws of refraction. Laws of refraction. The incident ray, the refracted ray and the normal to the surface lie in the same plane. The ratio of the sine of the angle of incidence I and the sine of the angle of refraction R is constant for a given pair of media. This rule is called Snell's law. Mathematically, Snell's law gives sine I by sine R is equal to n21, where n21 is a constant called the refractive index of medium 2 with respect to medium 1. If n21 is greater than 1, the refracted ray bends towards the normal. If n21 is less than 1, the refracted ray bends away from the normal. Higher the refractive index of a medium, the more it is optically denser. Apparent depth. Due to refraction, the object in another medium, say in water, appears to be raised. Total internal reflection. When a ray of light is incident on the boundary from denser to rarer medium, it is deviated away from the normal. With increase in an angle of incidence, the angle of refraction increases. For a certain angle of incidence in denser medium, the corresponding angle of refraction in rarer medium is 90 degrees. This particular angle of incidence, for which the corresponding angle of refraction is 90 degrees, is called the critical angle, denoted by C. If angle of incidence is increased beyond the critical angle, the incident ray is not refracted but returns in denser medium following the laws of reflection. This phenomenon is called the total internal reflection. Conditions for total internal reflection. The ray must pass from denser medium to rarer medium. The angle of incidence in the denser medium must be greater than the critical angle for the given pair of media. Relation between refractive indices of media and critical angle. If ND and N are the refractive indices of denser and rarer medium respectively, then from Snell's law, sine I by sine R is equal to NR upon ND. For critical angle incidence, I is equal to C and R is equal to 90 degrees. Therefore, sine C by sine 90 degrees is equal to NR by ND. It implies sine C is equal to NR by ND. If VR is speed of light in rarer medium and VD that in denser medium, then sine C is equal to VD by VR. Total internal reflection in nature and its technological applications. Mirage. In deserts, sometimes a man sees an inverted image of a tree, which gives a false impression of a pond of water near the tree. This is called mirage. sparkling of diamond. The critical angle for diamond-air interface is very small, nearly 24.4 degrees. When light from an external source enters in a well-cut diamond, it suffers multiple total internal reflections inside the diamond. When at any surface, the angle of incidence is less than 24.4 degrees, only then it may refract out. Thus, the light entering the diamond from all directions emerges out from some directions. Therefore, looking from these directions, the diamond appears sparkling. Prism. When a ray is incident normally on any refracting surface of prism, it passes undeflected and becomes incident on glass-air interface at angle 45 degree, which is greater than the critical angle 42 degree, and so suffers total internal reflection. A total reflecting prism may be used to deviate the rays through 90 degree, to deviate the rays through 180 degree, and to erect the inverted image without any deviation. Optical fiber. An optical fiber is a device based on total internal reflection by which a light signal may be transmitted from one place to another with a negligible loss of energy. Did you know? From 1670 to 1672, Newton lectured on optics. During this period, he investigated the refraction of light and reflection of light. Willebrord Snell gave his theory on refraction of light in 1621. Summary. Let us summarize what we have learned. A mirror formed from part of a spherical surface called a spherical mirror. The mirror equation: 1 by V plus 1 by U is equal to 1 by F. The phenomenon of the change in direction of a beam of light in one medium when it enters a second medium obliquely is called refraction. Snell's law gives sin I by sin R is equal to N21, where N21 is a constant called the refractive index of medium 2 with respect to medium 1. Conditions for total internal reflection. The ray must pass from a denser medium to a rarer medium. The angle of incidence in the denser medium must be greater than the critical angle for a given pair of media. Introduction.
Aditya, did you see my specs? I'm not able to see anything without them.
Yes, Grandpa. Here they are.
Now I can see. So how are you today?
I'm good, Grandpa. I want to ask you something.
Sure, ask me.
How do the specs help you to see clearly?
Actually, in the specs, the lenses are fitted with correct measurements. And with the help of them, I can see this beautiful world.
Can you tell me more of it?
Sure. Come with me. I'll tell you more about lenses in our new chapter, Ray Optics and Optical Instruments.
Objectives. At the end of this lesson, you will be able to explain refraction at spherical surfaces, use lensmaker's formula, find the position of image using thin lens formula, explain refraction through prism, explain dispersion by a prism, explain the working of human eye, explain the working of microscope, explain the working of telescope. Refraction at spherical surfaces and by lenses. Refraction at a spherical surface. The figure given shows a convex refracting surface separating two media. Let P be the pole and see the center of curvature of the refracting surface. Let N1 and N2 be the refractive indices of rarer and denser media respectively. Let O be a luminous point object on the principal axis of the convex refracting surface. An incident ray OA after refraction at the point A on the surface bends towards the normal NAC and goes along AI. Another ray OP falls normally on the surface and proceeds undeviated after refraction. The two refracted rays meet at I, which is the real image of point object O. The relation between object and image distance in terms of refractive indices of the medium and the radius of curvature of the curved spherical surface is N2 by V minus N1 by U is equal to N2 minus N1 by R. Refraction by a lens. Suppose L is a thin lens. The refractive index of the material of lens is N2 and it is placed in a medium of refractive index N1. The optical center of lens is C and x' is principal axis. The radii of curvature of the surfaces of the lens are R1 and R2 and their poles are P1 and P2. The thickness of lens is T, which is very small. O is a point object on the principal axis of the lens. The distance of O from pole P1 is U. The first refracting surface forms the image of O at I' at a distance V' from P1. The image I' acts as a virtual object for second surface, and after refraction at second surface, the final image is formed at I. The formula of refraction for thin lens is, this formula is called lens maker's formula. This formula also holds for concave lens. If the first medium is air and refractive index of material of lens be n, then N2 upon N1 is equal to n. And we know that. So the lens maker's formula can be written as, this is called thin lens formula. The focus on the side of the source of light is called the first focal point, whereas the other is called the second focal point. Magnification M for the lens is defined as the ratio of the size of the image to the size of the object. M is equal to H' by H is equal to V by U. Example. A 6 cm high object is placed at a distance of 30 cm in front of a concave lens of focal length 15 cm. Calculate the position of the image. Solution. Given U is equal to minus 30 cm, F is equal to minus 15 cm. Hence, from lens formula, 1 upon F is equal to 1 upon V minus 1 upon U. We have 1 upon V is equal to 1 upon F plus 1 upon U is equal to 1 upon minus 15 within parenthesis plus 1 upon minus 30 within parenthesis is equal to minus 1 upon 15 minus 1 upon 30 is equal to minus 3 upon 30, or V is equal to minus 30 upon 3 is equal to minus 10 centimeters. That is, the image will be formed on the side of the object at a distance of 10 centimeters from the lens. Power of a lens. The power of a lens is measured by its ability to deviate the rays towards the principal axis. The lens L2 has focal length less than L1. Therefore, lens L2 bends the rays more than L1. Hence, the power of the lens L2 is greater than that of L1. Clearly, P is directly proportional to 1 by F. In SI system, the focal length is in meter. The power of the lens is in diopter. Therefore, P is equal to 1 by F in meter, diopter D. Clearly, the power of a lens of focal length 1 meter is 1 diopter. Combination of thin lenses in contact. Suppose two thin convex lenses L1 and L2 are placed in contact in such a way that they have the same common axis. The focal lengths of lenses are f1 and f2 respectively, and the medium is same on both sides of lenses. O is a point object on the principal axis at a distance u from the first lens, L1. The lens L1 deviates the rays towards I. That is, I is the image formed by the first lens, L1 alone. If V' is the distance of image I' from the lens L1, then for lens L1, 1 by V' minus 1 by U is equal to 1 by F1, name it as equation 1. For lens 2, 1 by V minus 1 by V' is equal to 1 by F2, name it as equation 2. Add equation 1 and 2 and we get 1 by V minus 1 by U is equal to 1 by F, where 1 by F is equal to 1 by F1 plus 1 by F2. If the number of thin lenses are in contact of focal length F1, F2, F3, then the effective focal length of their combination is 1 by F is equal to 1 by F1 plus 1 by F2 plus 1 by F3 and so on. In terms of power, P is equal to P1 plus P2 plus P3 and so on. The total magnification M of the combination is a product of magnification M1, M2, M3 and so on of individual lenses. M is equal to M1, M2, M3. Refraction through a prism. A prism is a homogeneous, transparent medium enclosed by 3 vertical plane surfaces. 2 of these surfaces are usually polished and are called refracting surfaces, and the angle between them is called the angle of prism or refracting angle. The third surface, known as base, is usually grounded and does not allow the transmission of light. Let us consider the passage of a monochromatic light ray PQ through the glass prism ABC. At surface AB, when ray enters the glass at angle of incidence I, it bends towards the normal at Q at angle of refraction R1 and strikes the surface AC at R. The angle of incidence at surface AC is R2 and the ray emerges into air, making an angle E with the normal R. The emergent ray RS and the direction of the incident ray PQ is called the angle of deviation delta. The angle of deviation delta can be evaluated to delta is equal to I plus E minus A. For a given prism, A is fixed, angle of deviation delta depends on angle of incidence. As the angle of incidence is increased from very small volume, the angle of deviation first decreases, reaches a minimum and then increases. For the minimum deviation, I is equal to E, which implies R1 is equal to R2. Delta minimum is equal to 2I minus A. The refractive index of the material of the prism, N, is equal to sine of A plus delta minimum by 2 divided by sine of A by 2. Dispersion by a prism. The splitting of white light into constituent colors is called dispersion. The component of colors appear in the sequence are violet, indigo, blue, green, yellow, orange, and red. The angle of deviation for violet light will be maximum, and for red light it will be minimum. Therefore, when white light enters a prism, then the rays of different colors are refracted in different directions, and so they emerge from prism in different directions. Newton's classic experiment on dispersion of white light. The experiment performed by Sir Isaac Newton had put another prism, P2, in front of a prism P1, but inverted in position, and the emergent beam from the prism P1 on the prism P2, and the emergent beam from the prism P2 is a white light. Some natural phenomena due to sunlight. The rainbow. It is an example of dispersion of sunlight by the raindrops suspended in the atmosphere of the earth. This phenomenon arises due to combination of refraction and internal, not total reflection by spherical water droplets. Primary rainbow. When sunlight falls on raindrops, the different rays suffer different angles of deviation. Primary rainbow is formed when a ray undergoes 2 refractions and 1 internal reflection. The intensity is maximum for red rays at 42 degrees and violet rays at 40 degrees. Secondary rainbow. Secondary rainbow. When the sunlight falls on raindrops such that there are 2 refraction and 2 internal reflections, then secondary rainbow is also seen along with a primary rainbow. In this second rainbow, the violet color is deviated more than the red color. Scattering of light. When ordinary sunlight passes through atmosphere containing extremely small air molecules, dust and smoke particles, etc., it is deflected from its path due to interaction of electric field vector of light wave and the target particle. This phenomenon is called scattering, and the deflected light is called the scattered light. Rayleigh law of scattering. Rayleigh law of scattering. The intensity of light scattered from fine particles, dimensions wavelength of light, is inversely proportional to 4th power of wavelength of light, that is, why we see a blue sky most of the time. Sunlight reaches the Earth's atmosphere and is scattered in all directions by all the gases and particles in the air. But light is scattered in all directions by the tiny molecules of air and the Earth's atmosphere. Blue is scattered more than other colors because it travels a shorter waves. This is why we see a blue sky most of the time. Why the sun appears reddish at sunrise or sunset? As the sun gets lower in the sky, its light is passing through more of the atmosphere to reach you. Even more of the blue light is scattered, allowing the reds to pass straight through your eyes. Optical instrument, the eye. Our eye acts as a convex lens fixed in its place through muscles. This lens is called eye lens. The rays coming from a luminous body fall on eye lens and after refraction through it are focused on the retina. Thus, real, diminished and inverted image of the object is formed on the retina. Our mind feels this image erect. Power of accommodation of eye. On account of elasticity of muscles, the eye lens has the ability to change its focal length, which enables us to see near and distant objects. The power of eye lens is called the power of accommodation. The maximum distance at which an object placed can be seen distinctly by the eye is infinity. When the object is at infinity or very far from the eye, the parallel rays starting from it and after refraction through eye lens are focused on the retina and the object is clearly seen. In this state, there is no tension in muscles, that is, the eye is in relaxed state and the focal length of eye lens is maximum. When the object is near the eye lens, the muscles contract to increase the curvature or decrease the radius of curvature of the refracting surfaces of the lens. This causes decrease in focal length of the lens and again a clear message is formed on the retina. Thus the eye can clearly see the near and distant objects. The minimum distance up to which the eye can see clearly by exerting maximum pressure on muscles is called the least distance of distant vision. For normal eye, this distance is 25 centimeters and is denoted by D. For normal eye, the near point D is 25 centimeters and far point is infinity. Optical instrument, the eye. Pupil. The function of pupil is to control the quantity of light entering the eye. When light is strong, the pupil automatically contracts, and when light is weak, the pupil automatically dilates. This process is called adaptation. Persistence of vision. When an object is viewed by the eye, the impression produced on the retina does not disappear immediately after the object is removed from the front of eye. This impression persists for a short time, about 1/10 seconds. This is called the persistence of vision. The point where the optic nerve enters the eye is insensitive to light and is therefore known as blind spot. Defects of eye. Myopia or short-sightedness. Myopia is the defect of eye in which a person can see only nearer objects but fails to see farther objects distinctly. This defect is due to 1. Decrease in focal length of the eye lens. 2. Spreading of eye sphere. Remedy. To eliminate this defect, a concave lens of suitable focal length is used. Long-sightedness or hypermetropia. Hypermetropia is the defect of eye in which a person can see only farther objects but fails to see nearer objects distinctly. This defect is due to 1. Increase in focal length of eye lens. 2. Contraction of eye sphere. Remedy. To eliminate this defect, a convex lens of suitable focal length is used. Defects of eye. Presbyopia. In high growing age, the eye lens loses its flexibility of changing focal length. Consequently, the near point of eye is displaced farther and far point of eye is displaced nearer, so that the eye becomes unable to see nearer as well as farther object. This defect of eye is called presbyopia. This defect may be eliminated by using bifocal lenses. Astigmatism. The defect of eye in which horizontal and vertical objects at the same distance are not focused at the retina clearly is called astigmatism. The astigmatism is corrected by using cylindrical lens. The microscope. A microscope is a device to see nearer very small objects clearly. A simple microscope consists of a convex lens of small focal length. The principle of simple microscope is that if an object is placed between the lens and its first principal focus, the image formed by the lens is erect and magnified. Magnifying power of a microscope. M is equal to D into 1 by F1 by V. When final image is at a distance of distinct vision, that is V is equal to D, then M is equal to 1 plus D by F. When the final image is formed at infinity, then V is equal to infinity. M is equal to D into 1 by F, 1 by infinity, D by F. Compound microscope. It consists of long cylindrical tube containing at one end a convex lens of small aperture and small focal length. This is called the objective lens O. At the other end of the tube, another coaxial smaller and wide tube is fitted, which carries a convex lens E at its outer end. This lens is towards the eye and is called the eyepiece. The focal length and aperture of eyepiece are somewhat larger than those of objective lens. Cross wires are mounted at a definite distance before the eyepiece. The entire tube can be moved forward and backward by the rack and pinion arrangement. Magnifying power of a compound microscope. M is equal to minus V0 upon U0 into D upon Fe plus D upon Ve. Signs here already have been put. Telescope. The astronomical refracting telescope consists of an objective lens system and an eyepiece. However, the two instruments differ in that the objective of telescope has a large focal length and a much larger aperture. Light from the distant object enters the objective and a real image is formed within the tube. The eyepiece, used as a simple magnifier, leaves the final image inverted. When the final image is formed at infinity, the objective lens O collects parallel rays from the distant object. So, an image I is formed at the principal focus FO of the objective. Since the final image is at infinity, therefore, I must be at the principal focus FE of the eyepiece. Thus, FE and FO are at the same place. Magnifying power of a telescope in normal adjustment is the ratio of the angle subtended by the image at the eye as seen through the telescope to the angle subtended by the object as seen directly when both the object and the image are at infinity. The angular magnification is M is equal to minus FO by FE, where FO is the focal length of objective, FE is the focal length of the eyepiece. Did you know? Newton demonstrates that a prism could decompose white light into a spectrum of colors. Hubble Space Telescope helps find the most distant galaxies. Summary. Let us summarize what we have learned. The relation between object and image distance in terms of refractive indices of the medium and the radius of curvature of the curved spherical surface is n2 by v minus n1 by u is equal to n2 minus n1 by r. Lens maker's formula is this. Thin lens formula is this. Magnification M of the lens, M is equal to V upon U. Power of a lens, P is equal to 1 upon F in meters, diopter D. The combined power of thin lenses with power P1, P2, P3 is P is equal to P1 plus P2 plus P3 and so on. The refractive index of the material of the prism. n is equal to sine of a plus delta minimum by 2 divided by sine of a by 2, where a is the angle of prism and delta m is the minimum deviation. The splitting of white light into constituent colors is called the dispersion. The intensity of light scattered from fine particles, dimensions wavelength of light, is inversely proportional to fourth power of wavelength of light, that is, I directly proportional to 1 upon lambda raised to the power 4. Defects of vision are myopia, hypermetropia, presbyopia, and astigmatism. Magnifying power of a microscope, m is equal to d into 1 upon f, 1 upon v. Magnifying power of a compound microscope, m is equal to minus v0 upon u0 into d upon fe plus d upon ve. The angular magnification of telescope is m is equal to minus fo upon fe, where fo is the focal length of objective and fe is the focal length of the eyepiece.
तो मेरे प्यारे दोस्तों, ये था रे ऑप्टिक्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी हाइजेंस प्रिंसिपल और यंग्स डबल स्लिट एक्सपेरिमेंट जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम इंटरफेरेंस और डिफ्रैक्शन के पैटर्न्स देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम वेव ऑप्टिक्स के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Kamal and Deep are traveling in the train. Then, a train passes from the nearby track.
The train's whistle is so loud.
Yeah, it's really not tolerable.
I wanna ask you something.
Yes, Kamal, sure.
When the train passes us, the sound is loud, and when it moves away, the sound dies. Can you please explain me about this?
Okay, Kamal, I will tell you. This is due to the Doppler effect. The train producing sound waves was moving with respect to us. It causes an apparent shift in the frequency of sound waves for us. That's why sound rises when the train comes near us and dies when train goes away from us.
It's really interesting. I wanna know something more about this.
Students, today we will study about the wave optics. Objectives. At the end of this lesson, you will be able to define wave front, know Hagen's principle, understand refraction and reflection of plane waves, describe plane wave front in lens and prism, understand the Doppler effect, define electromagnetic waves, understand coherent and incoherent addition of waves, describe interference of light waves, explain Young's double slit experiment, explain conditions for sustained interference. Wave front. Wave front is defined as the locus of all the particles of a medium vibrating in the same phase at a given instant. A line perpendicular to a wave front is called a ray. The phase difference between any 2 points situated on the same wave front is zero. The shape of a wave front depends upon the shape of the source of disturbance. The distance from one crest to the next crest is equal to wavelength lambda. The phase difference between any 2 points in the same phase on 2 consecutive wave fronts is 2 pi. So, at any given crest and trough, the phase is 2n pi and 2n plus 1 pi respectively, where n is an integer. Types of wave fronts. There are different types of wave fronts which are given as spherical wave front. The wave front of light waves radiated by a point source may be represented by spherical surfaces concentric with the source. Plane wave front. At large distances from a point source, the spherical wave fronts are of very large radii and small portions of these can be considered planes. Cylindrical wave front. A line source can produce a cylindrical wave front coaxial with the source. Hagen's principle. Hagen's principle is a geometrical construction for finding the shape of a new wave front at some instant. According to this principle, every point of a wave front is a source of spherical secondary waves called wavelets, which spread out in all directions with the speed of propagation of the wave in that medium. The new wave front at a later instant is the surface tangent to the secondary wavelets called the envelope of the secondary wavelets. Laws of reflection at a plane surface. The angle of incidence is the angle between the incident ray and the normal, but the ray is perpendicular to the wavefront and the normal perpendicular to the surface. Hence, the angle of incidence is the angle between the incident wavefront AB and the surface PQ. Similarly, the angle of reflection is the angle between the reflected wavefront CD and the surface PQ. Now, from the geometry of triangles BAC and DAC, AD is equal to BC and AD is equal to AC. We can say that these are congruent triangles. Hence, the angle of incidence is equal to the angle of reflection. Also, the incident ray, the reflected ray, and the normal are all in the same plane. Hence, the wave theory has proved the laws of reflection at a plane surface. Reflection of plane waves. Consider a parallel beam of light incident on a plane surface separating two media. The planes AB, A1-B1 and A2-B2 are the positions of the incident wavefront at different instants. A Huygens wavelet originating from point B in the wavefront AB will move a distance b dash in the second medium in the same time that the wavelet from A expands in the first medium to include point A dash on the surface xy. Since the two wavelets have radii A dash and B dash are not in the same medium, they move with different speeds, say v1 and v2 respectively. Case 1. If medium 2 is optically denser than medium 1, then v1 is greater than v2 and hence A dash is greater than B dash. The ray is bent towards the normal. Case 2. If medium 2 is optically rarer than medium 1, then v1 is less than v2 and hence A dash is less than B dash. The ray is bent away from the normal. Distance A dash is equal to v1 is equal to lambda 1, the wavelength of light wave in medium 1. Distance B dash is equal to v2 is equal to lambda 2, the wavelength of light wave in medium 2. Therefore, v1 by v2 is equal to lambda 1 by lambda 2, or it can be written as v1 by lambda 1 is equal to v2 by lambda 2 is equal to nu. The above expression shows that the frequency of the light wave remains unchanged during refraction. The wavelength decreases when the light wave refracts into a denser medium and the wavelength increases when the light wave refracts into a denser medium. Plane wavefront in lens. Consider a plane wavefront ACB incident on a double convex lens. According to Huygens hypothesis, each point of the wavefront acts as a source of secondary waves. These secondary waves will travel through different thickness of the lens. The time taken by the secondary wave to travel through CP1 in air plus P1 P2 in lens will be the same as the time taken by waves to travel through AX plus XD in air. So, all the secondary waves from the incident plane wavefront ACB reach dP2E at the same time. Thus, dP2E is the refracted wavefront. This wavefront is converging in nature. Plane wavefront in prism. Consider a plane wavefront BD incident on the prism. According to Huygens hypothesis, each point of the wavefront acts as a source of secondary waves. These secondary waves will travel through different thicknesses of the prism. The time taken by a secondary wave to travel through distance BC in the material of the prism is the same as the time taken by a secondary wave to travel through a distance dA plus AE in air. The distance travelled in air is clearly greater than the distance travelled in prism. This is because the velocity of secondary wave in the material of the prism is less than that in air. All the secondary waves starting from BD reach CE at the same time. So, CE is the emergent wavefront. The Doppler effect. Consider when there is a medium and the source moves away from the observer, then latter wavefronts have to travel a greater distance to reach the observer. The time taken between the arrivals of two successive wavefronts is hence longer at the observer than is at the source. Thus, the frequency as measured by the source will be smaller. This is known as the Doppler effect. The Doppler effect is observed whenever the source of waves is moving with respect to an observer. The Doppler effect can be described as the effect produced by a moving source of waves in which there is an apparent shift in frequency for observer. redshift and blue shift. Redshift. The increase in wavelength due to Doppler effect is known as redshift because the wavelength in the middle of the visible region of the spectrum moves towards the red end of the spectrum. Blue shift. When waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. The Doppler shift is given by delta nu by nu is equal to minus v radial by c, where v radial is the component of the velocity along the line joining the source and observer. Electromagnetic waves. A wave of energy consisting of electric and magnetic fields is known as electromagnetic wave. Variations in both electric and magnetic fields occur simultaneously. As a result, they attain their maxima and minima at the same place at the same time. The directions of electric and magnetic fields are mutually perpendicular as well as to the direction of propagation of the wave. Thus, these waves are transverse in nature. The velocity of the waves depends entirely on the electric and magnetic properties of the medium in which these waves travel. Superposition of waves. Principle of superposition states that when two or more than two waves travel in the same medium at the same time superimposing each other, then the displacement of the resultant wave at any instant is equal to the vector sum of the individual displacements at that instant. Let vector y1, y2, y3 and so on be the displacement vectors due to the individual waves at any instant acting separately, then according to the principle of superposition, the displacement of the resultant wave at that instant is given by vector y1 plus y2 plus y3 plus so on. Coherent and incoherent sources of waves. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency and in same phase or having constant phase difference. There are two general methods for producing coherent sources are follows. By division of wavefront. In this method, the wavefront is divided into two or more parts by use of mirrors, lenses or prisms. By division of amplitude. In this method, the amplitude of incoming beam is divided into two or more parts by partial reflection or refraction. These divided parts travel different paths and are finally brought together to produce interference. Incoherent sources emit light with frequent and random changes of phase between the photons. Tungsten filament lamps and ordinary fluorescent tubes emit incoherent light. Interference of light waves. Interference of light is the phenomena of redistribution of light energy in the medium due to superimposition of light waves coming from two coherent sources. There are two types of interferences. They are constructive interference, destructive interference. The interference is constructive at the points where the resultant intensity of light is maximum, and the interference is destructive at the points where the resultant intensity of light is minimum. Constructive and destructive interference. Constructive interference. At the points of the medium where the resultant intensity of light is maximum, the interference is called as constructive interference. For constructive interference, phi is equal to 2n pi or p is equal to n lambda, where n is equal to 0, 1, 2, 3 and so on. Phi is equal to phase difference. P is equal to path difference. Lambda is equal to wavelength of light. Destructive interference. At the points of the medium where the resultant intensity of light is minimum, the interference is called as destructive interference. For destructive interference, phi is equal to 2n plus 1 pi or p is equal to 2n plus 1 lambda by 2. Young's double slit experiment. In Young's experiment, monochromatic light from a source passes through a narrow slit S and falls on two closely spaced narrow slits S1 and S2 placed at some distance from S. The slits S1 and S2 act as coherent sources of light waves because the light from each is derived from the same primary source S. These waves interfere constructively and destructively at different points on the screen to produce a pattern of alternating bright and dark bands called interference fringes on the screen. Mathematical analysis in Young's double slit experiment. Let S1 and S2 be coherent sources at separation D and capital D be the distance of screen from sources, then path difference between waves reaching at P is given by product of Yn and D divided by capital D. For maxima delta is equal to n lambda, position of nth maxima is given by n capital D lambda upon small d. Position of nth minima is given by n minus 1 upon 2 into capital D lambda upon small d. Fringe width. Fringe width is defined as the separation between two consecutive maxima or minima. Beta is equal to y into n plus 1 minus yn, which is equal to capital D lambda upon small d. Angular fringe width is given by beta upon d, which is equal to lambda upon d. Use of white light. When white light is used to illuminate the slit, we obtain an interference pattern consisting of a central white fringe having on both sides symmetrically a few colored fringes and then uniform illumination. Example. Let's take an example on Young's double slit experiment. The two slits in Young's experiment are 3 mm apart, illuminated by a light of wavelength 480 nanometer. The screen is at 2 meters from the plane of the slit. Find the separation between 8th bright and 3rd dark fringe with respect to central bright fringe. Let's see the solution. Distance of 8th bright fringe from center is given by 8 capital D lambda upon small d. Distance of 3rd bright fringe from center is given by 5 capital D lambda upon 2 small d. We have y is equal to y8 minus y3. By putting the values and calculating, we get y is equal to 11 capital D lambda upon small d. Putting the values in the above equation and calculating, we get value of y is equal to 3.52 millimeter. Hence, the separation between 8th bright and 3rd dark fringe with respect to central bright fringe is 3.52 millimeter. Conditions for sustained interference. The following conditions are necessary to obtain a continuous or permanent interference. the light should be monochromatic. If this is not so, the fringes of different colors will overlap. The two sources producing interference must be coherent. The wave trains causing the interference must have light waves of the same wavelength and same velocity. The two interfering wave trains must have the same plane of polarization. To observe interference fringes clearly, it is necessary that the fringe width is sufficiently large. Did you know? For manufacturing reasons, a perfect lens has a spherical surface shape, though theoretically the ideal surface should be aspherical. Light slows down, bends towards the normal, and has a shorter wavelength when it enters a higher refractive index or as it moves to denser medium. Reflection of waves of sea walls or other barriers can cause an interference pattern called a standing wave. In standing waves, crests do not move laterally. Summary. Let us summarize what we have learned. Wavefront is defined as the locus of all the particles of a medium vibrating in the same phase at a given instant. Every point of a wavefront is a source of spherical secondary waves called wavelets. The wavelength decreases when the light wave refracts into a denser medium. The Doppler effect is defined as the effect produced by a moving source of waves in which there is an apparent shift in frequency for observer. When waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. A wave of energy consisting of electric and magnetic fields is known as electromagnetic wave. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency, and in same phase or having constant phase difference. Interference of light is the phenomena of redistribution of light energy in the medium due to superposition of light waves coming from two coherent sources. Introduction. Tanuj, what are you doing? I'm searching one of the science educational DVD. Can you please help me in finding the DVD? Sure. Amit, can you please tell me something? Yeah, definitely. Why is this DVD shining in a rainbow pattern? What's the reason behind this colorful shine? Okay, I will tell you. It happens due to the diffraction of waves. Diffraction occurs when the wavelength of the wave are in order of the object size. The closely spaced tracks on the DVD are comparable with the wavelength of wave. That's why we observe the colorful shine of DVD. Okay, I got it. It's quite an interesting fact. Can you please tell me something more about this? I'm curious to know. Okay, let's today study more about the wave optics. Objectives. At the end of this lesson, you will be able to define diffraction, understand diffraction due to a single slit, differentiate between interference and diffraction, define resolving power, calculate resolving power of a microscope and telescope, define polarization and Polaroids, understand Malus law, describe polarization by scattering, reflection and refraction. Diffraction. Diffraction of light is the phenomena of bending of light waves around the edges of an obstacle or an aperture of size comparable to the wavelength of the incident light waves. Diffraction is of two types: Fresnel's diffraction and Fraunhofer's diffraction. In Fresnel's diffraction, source and screen are close to the obstacle and light after diffraction appears converging towards the screen, and hence no lens is required to observe it. In Fraunhofer's class, source and screen are at large distance from the obstacle. A converging lens is used to observe it. Diffraction due to a single slit. Consider a plane wavefront incident on the slit AB. Each point of the incident wavefront will be a source of secondary wavelets. These wavelets emanate from the wavefront in the same phase. To understand the formation of central maximum, the slit can be imagined to be divided into a number of very narrow strips of equal width parallel to the slit. All the wavelets originate from the narrow strip in the same phase. All these wavelets arrive at O in the same phase. These wavelets reinforce each other's effect to give maximum intensity at O. Now consider the formation of secondary minima and secondary maxima. Secondary wavelets diffracted at angle theta reaching a general point P on the screen. The wavelets shall not arrive at P in the same phase because these cover unequal distances in reaching P. Path difference between the extreme wavelets is given by Bn is equal to d sine theta. The condition for first secondary maximum is given at angle equals to 3 lambda upon 2d. The condition for second secondary maximum is given at an angle equals to 5 lambda upon 2d. Hence, the condition for nth maximum is given at an angle equals to 2n plus 1 lambda upon 2d. Width of secondary maximum is given by beta is equal to d lambda upon small d. Width of central maximum is given by beta naught is equal to 2d lambda upon small d. A distinct diffraction pattern is possible only if the slit is narrow. If the slit is made sufficiently large, then the secondary maxima will not be visible. Example. Let's take an example on diffraction pattern due to single slit. Determine the angular spread between central maximum and first order maximum of the diffraction pattern due to a single slit of width 0.25 mm when light of wavelength 5890 Armstrong is incident on it normally. Let's see the solution. We know that half the angular spread is given by a sine theta is equal to 2n plus 1 lambda by 2. On equating this, we get lambda by 2 is equal to 3 lambda by 2. When theta is small, then value of sine theta is equivalent to theta. It gives a theta is equal to 3 lambda by 2. On putting the values, we get the value of theta is equal to 3.530 multiplied by 10 raised to the power minus 3. Hence, the total angular spread is equal to 3.530 multiplied by 10 raised to the power minus 3 radians. Difference between interference and diffraction. Interference is the result of superposition of waves starting from two different wavefronts, whereas diffraction is the result of superposition of waves starting from different portions of the same wavefront. All bright fringes in an interference pattern are of same intensity, whereas intensity of brightness in a diffraction pattern decreases as one moves away from the central bright fringe. The points of minimum intensity in an interference pattern are perfectly dark, whereas the points of minimum intensity are not perfectly dark in a diffraction pattern. Resolving power. The ability of an optical instrument to produce separate images of two objects very close together is called resolving power. Rayleigh criteria. When the central maximum in the diffraction pattern of one point source falls over the first minimum in the diffraction pattern of the other point source, then the 2 point sources are said to have been resolved by the optical instrument. Resolving power of a lens. The resolving power of a lens is its ability to resolve 2 points that are close to each other. The resolving power is directly proportional to the aperture of the lens and inversely proportional to the wavelength of light used. Resolving power of a microscope. The resolving power of a microscope is defined as the reciprocal of the distance between two objects which can be just resolved when seen through the microscope. 1 upon delta D is equal to 2 mu sine theta upon lambda, where lambda is the wavelength of light, mu is the refractive index of the medium, and theta is the half angle of the cone of light from the point object. The term mu sine theta is called the numerical aperture of the objective. To increase the resolving power of a microscope, mu is increased by using suitable oil between the object and the objective. Resolving power of a telescope. Point-like sources separated by an angle smaller than the angular resolution cannot be resolved. A single optical telescope may have an angular resolution less than 1 arc second. The angular resolution of a telescope is given by R is equal to lambda divided by D, where lambda is the wavelength of the observed radiation and D is the diameter of the telescope's objective. Resulting R is in radians. Sources larger than the angular resolution are called extended sources and smaller sources are called point sources. The resolving power of a telescope is the reciprocal of the smallest angular separation between two distant objects whose images are separated in the telescope. D theta is equal to 1.22 lambda divided by A. A telescope with a larger aperture objective gives a high resolving power. Polarization. Polarization of light is the phenomena of restricting the vibrations of light in a particular plane. Plane polarized light is the light in which the vibrations of light are confined in a particular plane. Plane of vibration is the plane which is perpendicular to the plane of vibration. Polarizing angle is that angle of incidence at which the reflected light is completely plane polarized. Polaroids. Polaroid is a type of plastic sheet that can polarize a transmitted beam of normal light because it is composed of long parallel molecules. It only transmits plane polarized light if these molecules are parallel to the plane of polarization. Since reflected light is partly polarized, it is often used in sunglasses to eliminate glare. Linearly polarized light can be produced from unpolarized light with the help of Polaroid. The direction of polarization that a polarizing material allows through is called the transmission axis. Uses of Polaroids. Some important uses of Polaroids are following. It is used to avoid the glare of light. If we use sunglasses fitted with Polaroid, the eyes will not experience any glare. Polaroid sheets are fitted in car headlights and windscreen to avoid glare. Two Polaroid sheets are put one behind the other to control the light in window of aeroplane and big hotels. Camera used to photograph the clouds is fitted with Polaroid before the camera lens. Properly designed Polaroid glasses are used to produce and view a three-dimensional image. They are also used for studying optical properties of metals.
Malice's law. According to Malice's law, when completely plain polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axes of the analyzer and the polarizer. Suppose that theta is the angle between the transmission directions of the polarizer and analyzer. The intensity of the light transmitted by the analyzer varies with theta according to I equals I naught cos square theta, where I naught is the intensity of the light entering the analyzer.
Polarization by scattering. Consider an unpolarized light traveling along the y-axis strikes a gas atom at A. The electrons in the atom are set into oscillation in the xz plane by the oscillating E field of the incident wave. The radiation reaching O would come entirely from the dipole at A oscillating in the z direction and would be linearly polarized in the z direction. The transmitted radiation along y-axis is unpolarized because both dipoles can radiate equally well in the y direction. Sunlight scattered off atoms or molecules in the atmosphere of the Earth may also be polarized. If the atmosphere were not there, the sky would appear black except in the direction of the sun. Polarization by reflection. When light falls on the interface between two transparent media, it is partially reflected and partially refracted. The amount of light reflected or refracted depends on the polarization of the light relative to the interface. Consider an unpolarized light striking the interface between medium 1 and medium 2. At one particular angle, no light with polarization in the plane of incidence is reflected. All the reflected light is linearly polarized perpendicular to the plane of incidence. This angle of incidence is called the polarizing angle. Tan IP is equal to n, where n is the refractive index of the medium on which the light is incident. This equation is known as Brewster's law. Polarization by refraction. When ordinary light is incident on a glass plate at polarizing angle, the reflected light is plane polarized while the refracted component is partially polarized. Now, if this refracted beam is made to strike another glass plate at the polarizing angle, the same thing will be repeated at both the surfaces of glass plate. If the process is repeated using a number of parallel faced glass plates and light is incident on it at polarizing angle, then the beam emerging after refraction through these large number of plates will have almost all vibrations lying in the plane of incidence. The transmitted beam is thus plane polarized with vibrations in the plane of incidence. Did you know? Diffraction grating is an optical component with a regular pattern which splits light into several beams traveling in different directions. One consequence of diffraction is that sound from a loudspeaker will spread out rather than just going straight ahead. Sunglasses with polarizing films on them are used extensively while fishing and boating. These sunglasses are designed in such a way that one can look right through water. Reflection of waves of seawells or other barriers can cause an interference pattern called a standing wave. In standing waves, crests do not move laterally. Summary. Let us summarize what we have learnt. Diffraction of light is the phenomena of bending of light waves around the edges of an obstacle or an aperture of size comparable to the wavelength of the incident light waves. A distinct diffraction pattern is possible only if the slit is narrow. If the slit is made sufficiently large, then the secondary maxima will not be visible. The ability of an optical instrument to produce separate images of two objects very close to each other is called resolving power. The resolving power of a lens is its ability to resolve 2 points that are close to each other. Polarization of light is the phenomena of restricting the vibrations of light in a particular plane. Malus' law states that when completely plane polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of the cosines of angles between the transmission axis of the analyzer and the polarizer. When light falls on the interface between two transparent media, it is partially reflected and partially refracted.
तो मेरे प्यारे दोस्तों, ये था वेव ऑप्टिक्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी फोटो इलेक्ट्रिक इफेक्ट और दे ब्रॉगली वेवलेंथ जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम फोटोन और इलेक्ट्रॉन के नेचर को समझते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम डुअल नेचर ऑफ रेडिएशन एंड मैटर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। इससे पहले वाली फिजिक्स की वीडियो भी हमने ऑलरेडी कंप्लीट कर दी है, जिसे तुम प्लेलिस्ट में जाकर चेक कर सकते हो। इस लेक्चर के हैंडरिटन आईपैड नोट्स का लिंक डिस्क्रिप्शन में है और पूरी प्लेलिस्ट भी वहां मिल जाएगी। ओके।
Introduction. Look, Deepak, what I got. I have a torch. Yes, it is. But I don't think that you have better than mine. Look what I have. I have a laser light. Laser light. Wow, it is quite fascinating. You know, my father gifted me on my birthday. My father told me that this light is very dangerous for eyes. But how does a light can harm our eyes? Actually, it is a light of narrow frequency, and light has its application in the field of physics. Can you tell me more of it? Yes, sure. In this lesson, you will learn about the dual nature of matter and radiation. Objectives. At the end of this lesson, you'll be able to explain the electron emission, explain the photoelectric effect, discuss wave theory of light, state Einstein's photoelectric equation, find energy of photon, explain the particle nature of light, explain wave nature of matter, state Heisenberg principle, explain Davison and Germer experiment. Electron emission. In some solids called metals, the electrons, particularly outer ones, are so loosely bound to their parent atom that they can easily move from one atom to the other and move about in the solid. These electrons are called free electrons as they are free to move inside the solid but cannot leave the solid on their own. These electrons are held inside the metal surface by the attraction of the ions and of surface forces. Thus, these electrons require a certain amount of energy in order to come out of the metal surface. The minimum amount of energy required to emit electrons out of the metal surface is called the work function, phi0 of the metal. This minimum energy work function required for electron emission from the metal surface can be supplied to the metal in any of the following ways. Field emission. Electron can be made to leave the metal surface by applying strong electric field. Thermionic emission. By heating the metal, sufficient thermal energy is received by the free electrons to overcome the attractive pull of metal surface. Photoelectric emission. Free electrons from the metal can also be released by supplying energy to them in form of light. Photoelectric effect. The emission of electrons from metallic surface by light energy is called the photoelectric effect, and the electrons so emitted are called the photoelectrons. Hertz observations. While performing an experiment for production of electromagnetic waves by means of spark discharge, Hertz observed that sparks occurred more rapidly in the air gap of his transmitter when ultraviolet radiations was directed at one of the metal plates. Hertz could not explain these observations, but other scientists did it. They said that the cause was the emission of electron from metal plate due to incidence of high-frequency light. This is photoelectric effect. Hallwalks and Lenard's observations. Philip Lenard observed that when ultraviolet radiation was made incident on the emitter plate of an evacuated glass tube enclosing two metal plates called electrodes, current flows in the circuit. These observations indicate that when ultraviolet radiation fall on the emitter plate, the electrons are ejected from it, which are attracted to its anode plate. The electrons flow through the evacuated glass tube, completes the circuit, and current begins to flow in the circuit. Then Lenard and Hallwalks studied further by taking a zinc plate and an electroscope. The zinc plate was connected to an electroscope. They observed that when an uncharged zinc plate was irradiated by ultraviolet light, the zinc plate acquired positive charge. When a positively charged zinc plate is illuminated by ultraviolet light, the positive charge of the plate was increased. When a negatively charged zinc plate was irradiated by ultraviolet light, the zinc plate lost its charge. All these observations show that when ultraviolet light falls on zinc plate, the negatively charged particles, that is, electrons, are emitted. Experimental study of photoelectric effect, apparatus and circuit. The tube containing two electrodes, P and Q, has a side window of quartz to permit ultraviolet rays for the experiment. A source of radiation is suitably placed in front of the window such that the radiation falls on Q. P and Q are connected to a voltmeter with zero center. To provide the necessary voltage, We have a high tension battery B connected to across a potential divider arrangement Mn with a key K. Effect of intensity of light on photocurrent. The photoelectrons emitted per second is directly proportional to the intensity of incident radiation. Effect of potential on photoelectric current. Curve A is for low intensity of the incident radiation and curve B is for high intensity of the incident radiation. The photoelectric current increases with the increasing potential. For a certain potential, the current becomes maximum. After that, increase of potential does not increase the current, and that is called the saturation current. Let the potential of P be now made 0. At this stage, a small current is observed due to the few electrons which, just because of sufficiently large velocity of emission, are able to reach P, even though P does not have any positive accelerating voltage. Now let P be made negative by sliding the running contact L towards M. The current begins to fall off rapidly, and at a given fixed value of potential, minus V0, the current becomes 0, and the photoelectric emission will stop altogether. This voltage, V0, is called the stopping potential. Photocurrent is 0 when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy, Kmax, so that Kmax is equal to EV0. Effect of frequency of incident radiation on stopping potential. Photoelectric current remains unaffected by change of frequency, but stopping potential increases with increase of frequency of incident light. If we plot a graph for stopping potential V0 against frequency V of incident light, it is in the form of a straight line. If frequency is continuously decreased, the stopping potential becomes 0 at a certain frequency. This frequency is called the threshold frequency. Thus, threshold frequency is the minimum frequency of incident light at which the stopping potential or maximum kinetic energy of emitted electrons becomes 0. If the frequency of incident light becomes less than the threshold frequency, the photoelectric effect does not occur. Photoelectric effect and wave theory of light. According to wave theory, the kinetic energy of photoelectrons must depend on the intensity of incident light. But according to experimental observations, the kinetic energy of photoelectrons does not depend on the intensity of incident light. According to wave theory, the light of any frequency can emit electrons from metallic surface provided sufficient intensity of light. But according to the experimental observations, the light of frequency less than threshold frequency cannot emit electrons, whatever the intensity of incident light may be. According to wave theory, the energy transferred by light waves will not go to a particular electron, but it will be distributed uniformly, so emission of electrons will take some time. But experimental observations show that the emission of electrons take place instantaneously after the light is incident on the metal, whatever the intensity of light may be. Einstein's photoelectric equation. Energy quantum of radiation. Light propagates in the form of small bundles of energy called quanta or photons. The energy of each photon is h nu, where nu is the frequency of light and h is the Planck's constant. The value of h is 6.62 into 10 raised to the power minus 34 joule second. If the electron absorbs the energy from photon more than the energy needed to escape out from the metal surface, that is phi 0, then the electron is emitted with maximum kinetic energy K max, which is equal to h nu minus phi 0. This equation is known as Einstein's photoelectric equation. Important points. For the emission of electron from metal surface, h nu greater than phi 0. This shows that greater the work function phi 0, greater the threshold frequency needed to emit the electron. The more the number of photons available, the more the number of electrons absorbs energy from the photons, and therefore greater is the number of electrons emitted from the metal surface. We know that Kmax equals EV0 and Kmax is equal to h nu minus phi 0. So, h nu minus phi 0 is equal to EV0. VO is equal to h by E into nu minus phi 0 by E. If we plot a graph between nu and V0, taking nu on x-axis and Kmax on y-axis, the graph is a straight line, since equations is of the form y, which equals mx plus c. The slope of the line m is equal to h upon E, which is a universal constant. Example. If light of wavelength 4000 to 950 angstrom is viewed as a continuous flow of photons, what is the energy of each photon in eV? Given Planck's constant h as 6.6 into 10 raised to the power minus 34 joule second. Solution. The energy of photon can be found by E as h nu, E equals hc by lambda, name it as equation 1. C is the speed of light, which is 3 into 10 raised to the power 8 meter per second. From equation 1, E equals 6.6 into 10 raised to the power minus 34 into 3 into 10 raised to the power 8 by 4950 into 10 raised to the power minus 10 joule. After solving we get E as 4 into 10 raised to the power minus 19 joule. It can be expressed in eV, E as 4 into 10 raised to the power minus 19 by 1.6 into 10 raised to the power minus 19 eV. E is equal to 2.5 eV. Particle nature of light, the photon. The photoelectric effect supports the Einstein's quantum theory of light, which states that the light in interaction with matter behaves like bundles of energy, each bundle being called a photon. The photon picture of light can be summarized as, when radiation interacts with matter, it behaves as if it is made up of particles called the photons. The energy of each photon of frequency nu and wavelength lambda is E as h nu, which is equal to hc by lambda. The momentum of a photon P is equal to h nu by c, which equals h by lambda, where c is the speed of light. All photons of a given frequency have the same energy E, which is equal to h nu. The photons are electrically neutral, so they are not deflected by electric and magnetic fields. In photon-electron interaction, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision, because the photons may be absorbed and new photons of different energies may be created, so that total energy may remain constant, that is h nu, which equals h nu 1 plus h nu 2. Wave nature of matter. In 1924, Louis de Broglie proposed that material particles in motion behave as waves, and the wavelength associated with the material particles is given by lambda is equal to h by p, which equals h by mv, where p is equal to mv is the linear momentum of the moving particle. This is called de Broglie hypothesis. The momentum of the photon is p is equal to h by lambda. This gives wavelength lambda as h by p. Therefore, de Broglie proposed de Broglie wavelength lambda is equal to h by p, which equals h by mv. If k is kinetic energy of material particles, then the relation between momentum P and kinetic energy K is K as 1 by 2 mv square, which is equal to 1 by 2 into m into P by m square, which equals P square by 2m, or P as square root of 2mk. Hence, de Broglie wavelength lambda is equal to h by square root of 2mk, name it as 1. If V volt is the accelerating potential of electron, then K is equal to EV from equation 1. Lambda is equal to h by square root 2mev. Substituting the values of m, e and h, we get lambda as 12.27 by square root of V angstrom. Example. Calculate de Broglie wavelength associated with electrons accelerated through a potential of 5 kilovolt. Solution. Given V is equal to 5 kilovolt, which equals 5000 volt. From the formula given below, we can find the de Broglie wavelength. Lambda is equal to 12.27 by square root of V angstrom. Lambda plus is equal to 12.27 by square root 5000 angstrom, which equals 0.173 angstrom. Wave packet. According to Heisenberg, it is impossible to measure both the position and momentum of a material particle exactly at the same time. The product of uncertainties in simultaneous determination of position delta x and momentum delta p is of the order of h cap, where h cap is equal to h by 2 pi. Delta x into delta p approximately h cap. A wave of definite wavelength extends over all space, but an electron, which is represented by wave, cannot occupy all space. Therefore, it was suggested by Max Born that a material particle, say an electron, is not equivalent to a single wave, but it is equivalent to a wave packet, which is superposition of a number of waves of varying frequencies and results in a finite region where waves interfere constructively, and the particle has maximum probability of occurrence in this region. This region is called wave packet. Davison and Germer experiment. The given figure shows the set of Davison and Germer experiment. The electrons are accelerated to the desired energy by applying potential from a high-tension HT battery to a cylinder A having fine holes along its axis so that a fine beam emerges along the axis of the cylinder. The beam is directed at a block of nickel crystal known as the target T that is capable of rotating about an axis parallel to the incident beam direction. The electrons are scattered in all possible directions by the atoms of the crystal. The intensity of the scattered electron beam in a particular direction is measured with a Faraday cylinder called the collector C. The collector can be moved along a graduated cylinder scale S and is connected to a sensitive galvanometer. The deflection of the galvanometer is proportional to the intensity of scattered electron beam entering the collector. The variation of the intensity I of the scattered beam with the scattering angle theta is measured for various electron energies. From de Broglie relation, the de Broglie wavelength associated with the 54 eV electrons can also be determined. For these electrons accelerated through a potential difference of 54 V, lambda is equal to h by p, which equals 1.227 by square root of V. Nanometer is equal to 1.227 by square root of 54 nanometer equals 0.166 nanometer. The Davison-Germer experiment thus provides direct verification of de Broglie hypothesis of wave nature of material particles. Did you know? In 1905, Albert Einstein was a German-born theoretical physicist who explained the photoelectric effect. In 1924, Louis de Broglie gives his theory on wave-particle duality. Summary. Let us summarize what we have learned. The minimum amount of energy required to emit electrons out of the metal surface is called the work function phi0 of the metal. The energy can be supplied in three ways: field emission, thermionic emission, photoelectric emission. The emission of electrons from metallic surface by light energy is called the photoelectric effect, and the electrons so emitted are called the photoelectrons. Photoelectric current depends upon intensity of incident light, applied potential, frequency of incident light. Einstein's photoelectric equation. Kmax is equal to h nu minus phi 0, where Kmax is the maximum kinetic energy. Nu is the frequency of light. Phi 0 is the work function of the metal surface. Einstein's quantum theory of light states that the light in interaction with matter behaves like bundles of energy, each bundle being called a photon. The energy of each photon of frequency nu and wavelength lambda is E equals h nu. De Broglie wavelength lambda is equal to h by square root of 2 mk, where k is kinetic energy of material particles. Heisenberg principle states that it is impossible to measure both the position and momentum of a material particle exactly at the same time. The Davison-German experiment provides direct verification of de Broglie hypothesis of the wave nature of material particles.
तो मेरे प्यारे दोस्तों, ये था डुअल नेचर ऑफ रेडिएशन एंड मैटर का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी रुदरफोर्ड्स एक्सपेरिमेंट और बॉस मॉडल जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम रेडियस, वेलोसिटी और एनर्जी के फॉर्मूलास देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम एटॉम्स के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Today I'll teach you the topic structure of atom. Atoms are the fundamental units of matter. Everything around us is made up of atoms. A typical atom consists of a nucleus of protons and neutrons with electrons orbiting this nucleus. Sir, I have a question. All objects around us are made up of different materials. So how it is possible that atoms are fundamental unit of matter? Good question, Rakesh. As you know that all objects are made up of different material like plastic, rubber, iron, etc. They have different arrangement and types of molecules. And molecule is a group of two or more atoms. So the fundamental unit is atom. So students, let us discuss more about the atoms. Objectives. At the end of this lesson, you'll be able to know Thomson's model of atom, describe alpha particle scattering experiment, understand alpha particle scattering experiment, describe Rutherford's model of atom, define electron's orbit, analyze atomic spectra, describe Bohr's model of the hydrogen atom, know about energy levels of hydrogen atom, analyze line spectra of hydrogen atom, know about de Broglie's explanation of Bohr's second postulate. Thomson's model of atom. In 1898, J.J. Thomson suggested a model of atom, sometimes called plum pudding model. He supposed the atom to be full of some positive fluid, like a pudding, in which electrons were embedded like plumes in that pudding. The radius of this spherical model was about 10 raised to the power minus 8 centimeter. The total positive charge in the positive fluid was evenly and symmetrically balanced by the negative charges of the electrons. But this model was discarded because it failed to satisfy the result of the experiments performed by Rutherford. Alpha particle scattering experiment. Rutherford's experiments consisted in projecting alpha particles into thin foils of metal and by observing the trajectories in which the projected particles were deflected. Experimental setup. The alpha particles emitted from a radioactive source were collimated by the lead bricks into a narrow beam. The beam was then projected into a thin metal foil of thickness 2.1 into 10 raised to the power minus 7 meter. The scattered alpha particles on striking a rotable zinc sulfide screen produced scintillations which could be viewed through a microscope. Observations. Most of the alpha particles passed straight through the metal foil as if it were empty space. Only about 0.14% of the incident particles scattered by more than 1 degree. Small fractions were scattered through large angles greater than 90 degree, with some of these getting scattered by angles of nearly 180 degree. Rutherford developed a theory assuming that the alpha particle and the nucleus are point masses and charges. Only an electrostatic repulsive force acts between the alpha particle and the nucleus. The nucleus is so massive compared with alpha particle that it does not move during the interaction. Alpha particle trajectory. Since the electrostatic force varies with 1 upon r square, the alpha particle's trajectory is hyperbola, where r is the instantaneous separation between alpha particle and nucleus. The perpendicular distance between the nucleus and the initial line of motion of an alpha particle is called the impact parameter. Rutherford calculated the number n theta of alpha particles per unit area that reach the screen at a scattering angle of theta and found that n theta is inversely proportional to sin theta upon 2 raised to the power 4. The distance of closest approach between the particle and nucleus suggested the size of the nucleus to be about 10 raised to the power minus 14 meter to 10 raised to the power minus 15 meter. Any electrons belonging to the atom were assumed to be in the relatively charged volume outside the nucleus. With the atom being largely empty space, most alpha particles thus passed through the thin foil undeflected. Rutherford's model of atom. The Rutherford scattering experiment led to the nuclear atom model the main features of which are: an atom consists of a positively charged and massive core called the nucleus. The nucleus occupies a very small space as compared with the size of the atom. The nucleus is surrounded by an adequate number of electrons so that the atom is electrically neutral. To keep the electrons in place against the electric force attracting them to the nucleus, they revolve around the nucleus in orbits. Electrons orbit. The Rutherford nuclear model of the atom pictures the atom as an electrically neutral sphere consisting of a very small, massive and positively charged nucleus at the center, surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction between the revolving electrons and the nucleus provides the requisite centripetal force to keep them in their orbits. Fe is equal to Fc. Putting their respective values, we get mv square by r is equal to 1 upon 4 pi epsilon naught E square upon R square. We can also write this equation as R equals E square upon 4 pi epsilon naught mv square. The kinetic energy and electrostatic potential energy of the electron in hydrogen atom are given by K equals 1 upon 2 mv square, which equals E square upon 8 pi epsilon naught R, and U is equal to minus E square upon 4 pi epsilon naught R. Thus, the total energy of the electron in a hydrogen atom is given by E as K plus U, which is equal to minus E square upon 8 pi epsilon naught R. The total energy of the electron is negative. It means that the electron is bound to the nucleus. Atomic spectra. An evacuated glass tube filled with a glass such as hydrogen can be made to emit electromagnetic radiation by applying a sufficiently large potential difference between two electrodes located within the tube. If the emitted lines are analyzed, a series of discrete lines are observed, each line corresponding to a specific wavelength. Such a series of bright lines on a dark background is called an emission line spectrum. When white light passes through a gas, the transmitted light consists of some dark lines. These dark lines are called the absorption line spectrum of the material of the gas. The group of lines in the visible region is known as the Balmer series. These lines can be described by equation 1 upon lambda equals R 1 upon 2 square minus 1 upon n square. Here value of n may be 3, 4, 5 and so on, where R is Rydberg constant having value 1.0973732 into 10 raised to the power 7 per meter. The other series of lines exist outside the visible region are Lyman series, which is given by 1 upon lambda equals R 1 upon 1 square minus 1 upon n square. Here value of n may be 2, 3, 4, 5 and so on. Bastian series, which is given by 1 upon lambda equals R 1 upon 3 square minus 1 upon n square. Here value of n may be 4, 5, 6, 7 and so on. Bracket series, which is given by 1 upon lambda equals R 1 upon 4 square minus 1 upon n square. Here value of n may be 5, 6, 7, 8 and so on. Pfund series, which is given by 1 upon lambda equals R 1 upon 5 square minus 1 upon n square. Here value of n may be 6, 7, 8, 9 and so on. Bohr model of the hydrogen atom. The basic postulates of the Bohr model of the atom are: the electron moves about the nucleus under the influence of the Coulomb force in special circular orbits called the stationary orbits. In these orbits, electron does not radiate electromagnetic waves, hence the atom is stable. The stationary orbits are those for which the angular momentum L of the electron is an integral multiple of h upon 2 pi. L equals nh upon 2 pi, where n is known as quantum number of the orbit and h is Planck's constant. If the electron makes a transition from one stationary orbit to another stationary orbit, it emits a photon of frequency nu given by EI minus EF upon h. Radii of the Bohr orbits of hydrogen atom. We know that for hydrogen atom, radius of circular orbit is given by E square upon 4 pi epsilon naught mv square. We have to find the radius of nth orbit that satisfy the Bohr quantization condition on angular momentum. Ln is equal to product of m, Vn and Rn, which equals to nh upon 2 pi, where n is equal to 1, 2, 3 and so on. And Vn is the speed of the electron in nth orbit. This equation can be written as Vn equals nh upon 2 pi mRn. On comparing the above two equations, we get the expression of velocity and radius of nth orbit. Vn equals 1 upon n multiplied by E square upon 2 epsilon naught h, and Rn equals to n square multiplied by h square epsilon naught upon pi m E square, which equals n square A naught, where A naught is equal to 0.529 angstrom. Energy levels for hydrogen atom. We know that the total energy of hydrogen atom is the sum of the kinetic energy of the electron and its potential energy in the Coulomb field of the nucleus. En equals minus E square upon 8 pi epsilon naught Rn. This equation can also be written as En equals minus me raised to the power 4 divided by 8 epsilon naught square n square h square, where E naught is equal to me raised to the power 4 divided by 8 epsilon naught square h square. En equals 2.2 into 10 raised to the power minus 18 joule, which is equal to 13.6 electrovolt. The above equation can also be written as En equals minus 13.6 upon n square electrovolt. The energies specified by these equations are called the energy levels of the hydrogen atom. These levels are negative, signifying that hydrogen atom is a bound system. The lowest stationary energy state, called the ground state, corresponds to n as 1 and has an energy E1 equals minus 13.6 electrovolt. The next state, called the first excited state, corresponds to n as 2 and has an energy E2 equals minus 3.4 electrovolt and so on. As the quantum number increases, the corresponding energy approaches closer to zero. The minimum energy required to free the electron from the ground state of an atom is called the ionization energy of the atom. Thus, the ionization energy for hydrogen atom is 13.6 electrovolt. Example. Let's take an example of Bohr's model of the hydrogen atom. Let's see the solution. Find the ratio of minimum to maximum wavelength of radiation emitted by electron in ground state of Bohr's hydrogen atom. Energy of radiation corresponding to transition between two energy levels N1 and N2 is given by 13.6 multiplied by 1 upon N1 square minus 1 upon N2 square electrovolt. E is minimum when N1 is equal to 1 and N2 is equal to 2. E minimum is equal to 13.6 into 3 upon 4 electrovolt. E is maximum when N1 is equal to 1 and N2 is infinity. E maximum is equal to 13.6 electrovolt. Now taking ratio of E minimum and E maximum, we get E minimum upon E maximum as 3 upon 4, or lemma minimum, lemma max equals 3 upon 4. Hence, the ratio of minimum to maximum wavelength of radiation emitted by electron in ground state of Bohr's hydrogen atom is 3:4. The line spectra of hydrogen atom. In an assembly of atoms, an ordinary temperature, most of the atoms lie in the ground state. If white light is passed through such an assembly of hydrogen atoms, the transmitted light will not have radiations of various wavelengths. It is the absorption spectrum of hydrogen corresponding to Lyman series. An absorption spectrum is obtained when electron from lower energy state goes to higher energy state after absorbing energy from radiation. The frequency of absorbed radiation is given by h nu HL equals E high minus E low. At room temperature, there are very few electrons in higher energy states, N as 2 and 3. The number of electrons in various energy states is determined by the temperature. At higher temperature, hydrogen have sufficient number of electrons in state N as 2. The wavelength of absorption lines will be same as that of emission lines. This relation is used to calculate the frequency of absorbed light as that of emitted light. E2 minus E1 equals h nu 12, which is equal to hc upon lemma 12. de Broglie's explanation of Bohr's second postulate of quantization. De Broglie explained the quantization condition on angular momentum of an orbiting electron. According to de Broglie, when an electron is in a stationary orbit of an atom, it is in a kind of resonance. The resonance condition on the wavelength of the electron requires that a standing wave is maintained over the circumference of its orbit. Hence, the circumference of the electron's orbit contains an integral number of its de Broglie wavelengths. 2 pi r equals n lemma, where n is equal to 1, 2, 3, and so on. For an electron of mass m and speed v, the de Broglie wavelength is given by h upon mv. This may be written as mvr equals nh upon 2 pi. This is the Bohr's angular momentum quantization condition. Did you know? The number of atoms in the universe is about 10 followed by 80 zeros. Under certain conditions, atoms can be split into over 200 kinds of short-lived subatomic particles. The particles of the nucleus are made from various even tinier particles called quarks. In the 1890s, scientists thought that atoms were solid like billiard balls and completely unbreakable. Electrons are 1836 times as small as protons, so they weigh almost nothing. Summary. Let us summarize what we have learned. The distance of closest approach between the particle and the nucleus suggested the size of the nucleus to be about 10 raised to the power minus 14 meter to 10 raised to the power minus 15 meter. An atom consists of a positively charged and massive core called the nucleus. The nucleus occupies a very small space as compared with the size of the atom. The nucleus is surrounded by an adequate number of electrons so that the atom is electrically neutral. The electrostatic force of attraction between the revolving electrons and the nucleus provides the requisite centripetal force to keep them in their orbits. When white light passes through a gas, the transmitted light consists of some dark lines called the absorption line spectrum of the material of the gas. The electron moves about the nucleus under the influence of the Coulomb force in special circular orbits called the stationary orbits. The minimum energy required to free the electron from the ground state of an atom is called the ionization energy of the atom. An absorption spectrum is obtained when electron from lower energy state goes to higher energy state after absorbing energy from radiation.
तो मेरे प्यारे दोस्तों, ये था एटॉम्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई नीट ऑडियो मेंटोर। क्या तुम्हें भी मास डिफेक्ट और बाइंडिंग एनर्जी जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम रेडियो एक्टिविटी और हाफ लाइफ के फॉर्मूलास देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम न्यूक्लियाई के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लोग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लोग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Hi Rohit, what are you doing? Did you read the news of Cobalt-60? No, what happened? The radioactive material Cobalt-60 was found in Mayapuri, Delhi West. I don't know. And what is radioactive material? It is a kind of material which emits radiation which is harmful for life. Okay, so what happened at Mayapuri? They found radioactive material and a person was dead after getting in touch with radioactive material. That is very sad news. Over disadvantages, they do have favorable advantages. They are the bulk sources of energy. In this lesson, you will learn about the nuclear power generation. Objectives. At the end of this lesson, you will be able to define atomic mass, explain composition of nucleus, define size of the nucleus, state Einstein mass-energy relation, explain nuclear binding energy, explain nuclear force, explain alpha, beta and gamma decay, find half-life of radioactive material, explain fission and fusion, and explain the nuclear reactor. Atomic masses and composition of nucleus. The number of molecules in 1 mole of carbon is 6.02 into 10 raised to the power 23. That is Avogadro number. Since carbon is monoatomic, therefore there are 6.02 into 10 raised to the power of 23 atoms of carbon. They have a mass of 12 gram. Hence, mass of one atom of carbon is equal to 12 by 6.02 into 10 raised to the power of 23 gram, which is equal to 12 by 6.02 into 10 raised to the power of 26 kilogram. Hence, 1 atomic mass unit AMU is equal to 1 by 12 into 12 by 6.02 into 10 raised to the power of 26 kilogram whole, which is equal to 1.6605 into 10 raised to the power minus 27 kilogram. Atomic mass is conventionally expressed in atomic mass units, such that the mass of the most abundant type of carbon atom is, by definition, exactly 12 atomic mass unit. Composition of nucleus. Rutherford's experiment on the scattering of alpha rays led us to conclude that an atom has a tiny central hard core. Nearly the whole mass of the atom is concentrated in this core. This central core is named as nucleus. Every atomic nucleus contains basically two types of particles, protons and neutrons. The single exception is that of nucleus of hydrogen. This nucleus contains only one proton. The total number of protons in atomic nucleus is equal to total number of electrons in atom. So, the total amount of negative charge present in atom is equal to the total amount of positive charge in the atom. This makes the atom as a whole electrically neutral. The composition of nucleus can be considered as: let Z be atomic number, which is equal to number of protons. Let N be neutron number, which is equal to number of neutrons. Let A be mass number, which is equal to Z plus N, which is equal to total number of protons and neutrons. Nuclear species are shown by the notation, where X is the symbol of nuclear species. The atoms of an element having same atomic number, that is Z, but different mass numbers are called isotopes. For example, isotopes of hydrogen are discovery of neutron. A is a disk having a radioactive source, polonium, which gives out alpha particles. B is the target of beryllium. Both A and B are placed in an evacuated chamber C. The beryllium plate issued out strong rays, which on falling at a block of paraffin gave out high energy protons. The nuclear reaction for the production of neutrons is expressed as size of the nucleus. It has been confirmed by various experiments that the nucleus does not have a sharp or well-defined boundary. However, the nucleus radius r can be given by r is equal to r0 into cube root of a, where r0 is equal to 1.2 into 10 raised to the power minus 15 m is a constant, which is the same for all nuclei, and a is the mass number of the nucleus. Mass energy. Einstein gave the mass energy equivalence relation. E is equal to mc square, where energy E is equivalent of mass m. C is the velocity of light in vacuum, that is 3 into 10 raised to the power 8 meter per second. Nuclear binding energy. Mass defect. It is found that the mass of a stable nucleus is less than the total mass of its nucleons, that is protons and neutrons. This difference delta m in mass is called mass defect and is given by delta m is equal to ZMP plus A minus Z into Mn minus M, where Mp and Mn are the masses of proton and neutron respectively. M is the actual mass of nucleus. A is the mass number. Z is the atomic number. The energy equivalent to the mass defect, that is delta M into C square, is the binding energy, EB, of the nucleus. From the graph, we note that binding energy per nucleon increases with A, and after attaining flat maximum, it decreases gradually. Nuclei with intermediate mass number have highest energy per nucleon. For mass number 56, the binding energy per nucleon is highest. At a multiple of 4, that is corresponding to mass numbers 4, 8, 12 and 16, the binding energy per nucleon shows a sudden raise. This is particularly marked in the lighter elements. The average binding energy per nucleon is 8 MeV. For lighter and heavier elements, the binding energy per nucleon is less than the average value. Nuclear force. It is the nuclear force which binds the nucleons together and is responsible for the stability of nucleus. Properties of nuclear force. They are ordinarily attractive. They are charge independent. They are short-range forces. They are spin dependent. They are non-central forces. and the nuclear force is the strongest of the three fundamental forces that are gravitational, Coulomb, and nuclear force. Radioactivity. Unstable nuclei can often transmute into other nuclei through the emission of alpha, beta, or gamma particles. Any such spontaneous transition from one state to another is known as a radioactive decay. There are three types of radioactive decay: alpha decay, beta decay, and gamma decay. Law of radioactive decay. If n denotes the number of radioactive nuclei of any specified type at a given time, and lambda is the constant probability for decay per unit time, that is, decay constant, then the change in the number of nuclei during an infinitesimal time interval dt is defined by dn is equal to n t plus dt whole minus n t, which is equal to minus nt lambda dt. The negative sign indicates that nuclei decreases as a result of decay. Let n naught be the initial number of nuclei at t is equal to 0. Then nt, that is number of nuclei at any time t, is written as nt is equal to n naught into a raised to the power minus lambda t. Let r be the decay rate, which can be defined as r is equal to minus dn by dt. Name it as equation 1. Differentiating equation 1, we get r is equal to lambda n naught e raised to the power minus lambda t. Let lambda n naught equal to r naught. R is equal to r naught e raised to the power minus lambda t. Here, r naught is the decay rate at t is equal to 0, and r is the decay rate at any time t. The rate of disintegration of a radioactive element is called its radioactivity or simple activity. It is denoted by R. Activity can be expressed as R is equal to n lambda. The SI unit for activity is becquerel. 1 becquerel is equal to 1 BQ is equal to 1 decay per second. Radioactivity. The time interval T12 during which half of the nuclei in the sample decay is called half-life. T12 is equal to N2 by lambda, which is equal to 0.693 by lambda. The mean or average life of a radioactive material is tau, which is equal to 1 by lambda. Example: carbon has a stable isotope carbon-12 and a radioisotope carbon-14 present in the ratio 1:1.4 into 10 raised to the power minus 12. The half-life of carbon-14 is 5,730 years. Find the activity of 1 gram of carbon sample. Avogadro's number is equal to 6 into 10 raised to the power 23. Solution: the number of atoms in 1 gram carbon is equal to 6 into 10 raised to the power 23 whole by 12, which is equal to 5 into 10 raised to the power 22. The number of carbon-14 atom in 1 gram carbon is equal to 1.4 into 10 raised to the power minus 12 into 5 into 10 raised to the power 22, which is equal to 7 into 10 raised to the power 10. Hence, activity of the sample R is equal to lambda n, which is equal to 0.693 by T half into N, which is equal to 0.693 into 7 into 10 raised to the power 10 by 5730 into 365 into 24 into 3600, which is equal to 0.26 per second per gram, approximately 16 per minute per gram. Alpha decay. Alpha particle is nucleus of a helium atom having atomic number 2 and atomic weight 4. It is denoted by, therefore, when an alpha particle is emitted from a radioactive parent atom X, its atomic number is reduced by 2 and atomic weight is reduced by 4. It can be demonstrated as the energy Q released in this process can be obtained from Einstein's mass-energy relation. It is given by the equation Q is equal to mx minus my minus mhe into c square. This energy is shared by the daughter nucleus and the alpha particle. For example, beta decay. A nucleus with an overabundance of neutrons can transform to a more stable nucleus by emitting an electron or a positron. This kind of process is known as beta decay. This process of beta decay can be expressed as where is the beta particle and is the antineutrino. For example, in some artificial disintegration, positrons are also emitted from the nucleus. Antineutrino and neutrino both are massless and chargeless particle and is emitted to conserve energy and momentum. Gamma decay. To explain the emission of gamma rays from nucleus, it is assumed that a nucleus possesses certain discrete energy states. When an alpha particle or a beta particle is emitted from the nucleus, the residual nucleus is left in an excited state. The excited nucleus returns to ground state by emitting a gamma photon, whose energy is equal to difference of energies of two nuclear states. For example, cobalt nucleus with mass number 60 and atomic number 27 transforms into nickel nucleus with mass number 60 and atomic number 28 in its excited state. The excited nickel nucleus with mass number 60 and atomic number 28 returns into ground state by emission of two successive gamma photons of energies 1.17 MeV and 1.33 MeV. Nuclear energy. Changes can occur in the structure of the nuclei of atoms. These changes are called nuclear reactions. Energy created in a nuclear reaction is called nuclear energy or atomic energy. Fission. The splitting of a heavy nucleus into two lighter nuclei is called the nuclear fission. When a slow neutron strikes a uranium-235 nucleus, it is absorbed by the nucleus and an unstable isotope of uranium U-236 is formed, which immediately breaks into two fragments emitting 2 or 3 neutrons with release of enormous amount of energy. The reaction may be expressed as nuclear energy. A chain of reaction refers to a process in which neutrons released in fission produce an additional fission in at least one further nucleus. This nucleus in turn produces neutrons, and the process repeats. The process may be controlled, that is nuclear power, or uncontrolled, that is nuclear weapons. Controlled chain reaction. If the chain reaction is arranged artificially, such that out of 2 or 3 neutrons produced per fission, on the average, only one neutron causes further fission, so that the rate of fissions may remain constant, then the chain reaction is said to be controlled. Uncontrolled chain reaction. In this process, out of 2 or 3 neutrons produced per fission, on the average, more than one neutron cause further fission, and so there is no control on fission process. Thus, this is a very fast reaction, and huge amount of energy is released in a very short duration, and takes the form of a violent explosion. Thus, this energy is harmful and forms the principle of atom bomb. Reproduction factor. It is defined as the ratio of rate of production of neutrons to the rate of loss of neutrons. For chain reaction to take place, the reproduction factor should be greater or equal to 1. If the value of reproduction factor F is 1, the chain reaction is said to be steady. Nuclear reactor. Nuclear reactor is an important device which is based on controlled chain reaction and is a source of nuclear energy utilized for useful purposes. Fuel made up of heavy atoms that split when they absorb neutrons is placed into the reactor vessel, basically a large tank, along with a small neutron source. The neutrons start a chain reaction where each atom that splits releases more neutrons than cause other atoms to split. Each time an atom splits, it releases large amount of energy in the form of heat. The heat is carried out of the reactor by coolant, which is most commonly just plain water. The coolant heats up and goes off to a turbine to spin a generator or drive shaft. So basically, nuclear reactors are exotic heat sources. Production of plutonium. Some fast neutrons produced in the reactor are absorbed by uranium-238. As a result, it is converted into an unstable isotope, uranium-239. Uranium-239 emits a beta particle and is converted to neptunium-239. Neptunium also emits a beta particle and is spontaneously converted into plutonium-239. Nuclear fusion, energy generation in stars. The phenomenon of combination of 2 or more light nuclei to form a heavy nucleus with release of enormous amount of energy is called the nuclear fusion. Now we consider 2 deuterons to form a tritium. The tritium so formed can further combine with the third deuteron to form an alpha particle. The net result is most of the liberated energy appears in the form of kinetic energies of protons and neutrons. Controlled thermonuclear fusion. The combination of atomic nuclei at high temperatures to form more massive nuclei with the simultaneous release of energy. Thermonuclear fusion is the power source at the core of the Sun. Did you know? Anil Kakodkar is an eminent Indian nuclear scientist. He said, nuclear power is actually as safe as air travel, even though people perceive it as dangerous. Kakodkar also said that the catastrophe syndrome, which accompanies the word nuclear plant, needed to be put in perspective, especially to population groups and civil society activists who have been opposing nuclear power in India. Summary. Let us summarize what we have learnt. Atomic mass is conventionally expressed in atomic mass units. 1 atomic mass unit, or EMU, is equal to 1.6605 into 10 raised to the power minus 27 kilogram. Every atomic nucleus contains basically two types of particles, protons and neutrons. The radius of nucleus r is given by, where r0 is equal to 1.2 into 10 raised to the power minus 15 m is a constant, and A is the mass number of the nucleus. Einstein mass-energy equivalence relation, where energy E is equivalent of mass m. C is the velocity of light in vacuum, that is 3 into 10 raised to the power 8 meter per second. The mass of a stable nucleus is less than the total mass of its nucleons. This difference delta m in mass is called mass defect and is given by the energy equivalent to the mass defect, that is delta m, into c square is the binding energy, Eb, of the nucleus. Nuclear force is the force which binds the nucleons together and is responsible for the stability of nucleus. The decay rate can be expressed as, here R0 is the decay rate at t is equal to 0 and R is the decay rate at any time t. The rate of disintegration is called activity. It can be expressed as, the SI unit for activity is becquerel. The time interval t½ during which half of the nuclei in the sample decay is called half-life. The mean or average life of a radioactive material is, the splitting of a heavy nucleus into two lighter nuclei is called the nuclear fission. The phenomenon of combination of two or more light nuclei to form a heavy nucleus with release of enormous amount of energy is called the nuclear fusion.
तो मेरे प्यारे दोस्तों, ये था न्यूक्लियाई का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी पीएन जंक्शन, फॉरवर्ड बायस और रिवर्स बायस जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम हाफ वेव और फुल वेव रेक्टिफायर के डायग्राम्स देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम सेमीकंडक्टर इलेक्ट्रॉनिक्स के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लोग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लोग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Raj and Amar are sitting in the drawing room. Raj is reading his favorite book and Amar is doing some work. Amar, I want to ask you something. How this calculator works? How every time it gives the correct result? Okay Raj, I will tell you. Calculator works on the combination of diodes. Diode is a semiconductor device and it can be used for on and off purpose. When the diodes arranged in a particular manner, then they give specific logical result. Okay, Amar, now I understand the basic concept of calculator. It's quite interesting and I want to know something more about it. Students, today we will study about the semiconductor electronics. Objectives. At the end of this lesson, you will be able to know about energy bands in solids, define insulators, semiconductors and metals, understand intrinsic and extrinsic semiconductor, define N-type and P-type semiconductor, understand P-N junction, describe semiconductor diode, analyze forward and reverse biased junction diode, analyze VI characteristic of PN junction diode, define rectifier, explain Zener diode. Energy bands in solids. Electrons in an atom are distributed in various shells according to certain scheme and they are allowed to possess certain discrete energy values. The permissible energy values are usually shown on an energy level diagram. We consider the formation of bands for the energy level normally occupied by the valence electrons and the next level above it. The interatomic separation is supposed to decrease gradually from infinity to R, not corresponding to equilibrium separation in a crystal. Valence band. The valence band is a band of energy levels occupied by the bond valence electrons of the atoms in the crystal. Forbidden gap. A range of energies above the valence band which electrons are not allowed to possess. Conduction band. A band of energy levels just above the forbidden gap which is occupied by conduction electrons of the crystal. These electrons are free to move about and increase their energies in electric field. Insulators, semiconductors and metals. On the basis of band theory of solids, the solids are classified as insulators, semiconductors and metals. Insulators. Valence band filled completely and conduction band is far away. A good example of this type of material is diamond. It has a forbidden gap of 6 electrovolt. All the valence electrons take part in the covalent bond formation and none is available for conduction of electricity. Semiconductors. Valence band filled completely and conduction band is close to it. An example of this type of material is silicon. It has a forbidden gap of 1.1 electrovolt. At absolute zero it behaves like an insulator. But at room temperature, a small proportion of electrons gain enough energy from thermal vibrations of atoms so that they move to the conduction band. The conductivity of semiconductor material increases with rise in temperature. Metals. Valence band partially filled or valence and conduction band overlap each other. An example of this type of material is sodium. When an electric field is applied across a sodium crystal, electrons in the valence band can acquire small amount of energy as higher energy levels are available. The material is, therefore, a good conductor of electricity. In a good conductor, the partially filled valence band is also the conduction band. Intrinsic semiconductor. Intrinsic semiconductor are those in which impurities are not present and therefore called pure semiconductors. In these semiconductors, few crystals defect may be present. When a semiconductor is taken at 0 Kelvin, then it behaves as an insulator and conduction occurs at higher temperature due to thermal excitation of electrons from the valence band to the conduction band. For example, germanium and silicon. Let us consider silicon, which has 4 valence electrons. In order to gain stability, it has to make 4 covalent bonds. The electrons which are participating in the covalent bonds are known as valence electrons. If some energy is supplied, then covalent bonds break. Electrons will come out and move freely, resulting in the formation of vacant sites in the covalent bonds. These are known as positive charge carriers, named as holes. The number of conduction electrons will be equal to the number of vacant sites in the valence band. Extrinsic semiconductor. The extrinsic semiconductors are those in which impurities of large quantity are present. The impurities can be either of third group elements or fifth group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into 2 categories. N-type semiconductors. When a pentavalent impurity is doped in a pure semiconductor crystal, then the crystal is known as N-type semiconductor. P-type semiconductor. When a trivalent impurity is doped in a pure semiconductor crystal, then the crystal is known as P-type semiconductor. N-type semiconductor. N-type semiconductors. In order for silicon crystal to conduct electricity, we need to introduce an impurity atom such as arsenic, antimony, or phosphorus into the crystalline structure. These atoms have 5 outer electrons in their outermost covalent bond to share with other atoms and are commonly called pentavalent impurities. This allows 4 of the 5 electrons to bond with its neighboring silicon atoms, leaving 1 free electron to move about when electrical voltage is applied. As each impurity atom donates 1 electron, pentavalent atoms are generally known as donors. The resulting semiconductor material has an excess of current-carrying electrons, each with a negative charge, and is therefore referred to as N-type material, with the electrons called majority carriers and the resultant holes minority carriers. P-type semiconductor. P-type semiconductors. In P-type semiconductor, we introduce a trivalent impurity into the crystal structure, such as aluminium, boron, or indium. Only 3 valence electrons are available in the outermost covalent bond, means the 4th bond cannot be formed. It gives the semiconductor material an abundance of positively charged carriers known as holes in the structure of the crystal. As each impurity atom generates a hole, trivalent impurities are generally known as acceptors. The conduction mainly consists of positive charge carrier, results in a p-type material, and the positive holes are called majority carriers while the free electrons are called minority carriers. Example on semiconductors. Let's take an example on semiconductors. A semiconductor has equal electron-hole concentration of 6 × 10⁻⁸ per meter cube. On doping with a certain impurity, electron concentration increases to 8 into 10 raised to the power 12 per meter cube. Let's see the solution. As the electron concentration increases, it is an N-type semiconductor. We know that Ni square is equal to product of Ne and NH, where Ni is concentration of intrinsic carriers, NH is hole concentration, and Ne is electron concentration. Therefore, NH is equal to Ni square divided by Ne. On putting the values, we get NH is equal to 4.5 into 10 raised to the power 4 per meter cube. Hence, the new hole concentration is 4.5 into 10 raised to the power 4 per meter cube. With the doping, energy gap decreases. P-N junction. If donor impurities are introduced into one side and acceptor impurities into the other side of a pure crystalline semiconducting material, a P-N junction is formed. The donor ion is indicated by a positive sign because after this impurity atom donates an electron. It becomes a positive ion. The acceptor ion is indicated by a minus sign because after this atom accepts an electron, it becomes a negative ion. Initially, there is abundance of holes in the p-type material and of electrons in the n-type material. The holes in the p region will diffuse to the right across the junction and combine with electrons in the n region. Similarly, the electrons in the n region will diffuse to the left across the junction and combine with the holes in the p region. For every such diffusion recombination event, the left side of the junction acquires a negative charge and the right side a positive charge. As a result, an electric field will appear across the junction. Since the region of the junction is depleted of mobile charges, it is called the depletion region or the space charge region. To diffuse from the n region to the p region, an electron must climb the energy hill of height eV0. A hole must also climb an energy hill of the same height to diffuse from the p region to the n region. Semiconductor diode. A semiconductor diode is basically a p-n junction with metallic contacts provided at the ends for the application of an external voltage. It is a two-terminal device. The arrowhead corresponds to the p-type terminal of the device and points in the direction of easy current flow. It is a two-terminal electronic component with low resistance to current flow in one direction and high resistance in the other. The most common function of a diode is to allow an electric current to pass in one direction, while blocking current in the opposite direction. Forward-biased junction diode. When a diode is connected in a forward bias condition, a negative voltage is applied to the n-type material and a positive voltage is applied to the p-type material. If this external voltage becomes greater than the value of the potential barrier, the potential barrier's opposition will be overcome and current will start to flow. Forward biasing condition represents the low resistance path through the p-n junction, allowing very large currents to flow through the diode with only a small increase in bias voltage. The actual potential difference across the junction or diode is kept constant by the action of the depletion layer. The negative voltage pushes or repels electrons towards the junction, giving them the energy crossover and combines with the holes being pushed in the opposite direction towards the junction by the positive voltage. The application of a forward biasing voltage on the junction diode results in the depletion layer becoming very thin and narrow, which represents a low impedance path through the junction, thereby allowing high currents to flow. The point at which this sudden increase in current takes place is represented on the static IV characteristics curve as the knee point. Reverse biased junction diode. When a diode is connected in a reverse biased condition, a positive voltage is applied to the N-type material and a negative voltage is applied to the P-type material. The positive voltage applied to the N-type material attracts electrons towards the positive electrode and away from the junction, while the holes in the P-type end are also attracted away from the junction towards the negative electrode. The result is that the depletion layer grows wider due to a lack of electrons and holes and presents a high impedance path, almost an insulator. Reverse bias condition represents a high resistance value of the PN junction and partially zero current flows through the junction diode with an increase in bias voltage. However, a very small leakage current does flow through the junction, which can be measured in microamperes. PI characteristic of PN junction diode. In forward bias, the current first increases very slowly till the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases exponentially, even for a very small increase in the diode bias voltage. This voltage is called the threshold voltage or knee voltage. For the diode in reverse bias, the current is very small and almost remains constant with change in bias. It is called reverse saturation current. At very high reverse bias, the current suddenly increases. This voltage is called the breakdown voltage. Rectifier. The process of conversion of alternating current into direct current is called rectification, and the circuit for this conversion is called a rectifier. The crystal diode is used as a rectifier. There are two rectifier circuits in use. Half-wave rectifier. In half-wave rectifier, either the positive or negative half of the AC wave is passed while the other half is blocked. Full-wave rectifier. A full-wave rectifier converts the whole of the input waveform to one of constant polarity at its output. Half-wave rectifier. The AC signal to be rectified is connected across the primary terminals P1 and P2 of a step-down transformer. One of the secondary terminals S1 is connected to P region of junction diode, while the other secondary terminal S2 is connected to N region with a load resistance RL in series. The output voltage is taken across the load resistance RL. The AC input voltage across secondary terminals S1 and S2 changes polarity after each half cycle. During the first half cycle of input AC voltage, the terminal S1 is positive with respect to S2. During this half cycle, the diode is forward biased and therefore the diode conducts current from A to B. During the next half cycle, the terminal S1 is negative with respect to S2. Under this condition, the diode is reverse biased and therefore it conducts no current. Hence, a potential difference across load resistance RL exists for positive half cycles and no potential difference exists during negative half cycles. And the output across load is pulsating DC. Full wave rectifier. Full wave rectifier. For full wave rectification, two junction diodes are used. It consists of two diodes D1 and D2 whose N terminals N1 and N2 have been connected together. The AC signal to be rectified is connected across the primary terminals P1 and P2 of a power transformer. The P regions P1 and P2 of the diodes are connected to the ends S1 and S2 of the secondary of the transformer. The output taken across the load RL. The AC input voltage across secondary S1 and S2 changes polarity after each half cycle. During the first half cycle of input AC signal, the terminal S1 is positive and S2 is negative. Then, diode D1 is forward biased and diode D2 is reverse biased. Therefore, diode D1 conducts while diode D2 does not. The direction of current due to diode D1 is directed from A to B. In next half cycle, the terminal S1 is negative and S2 is positive. The diode D1 is reverse biased and diode D2 is forward biased. Therefore, diode D2 conducts while D1 does not. The direction of current due to diode D2 is from A to B. Thus, for input AC signal, the output current is a continuous series of unidirectional pulses. Zener diode. A Zener diode is a reverse biased properly doped crystal diode having a sharp breakdown voltage and operated in breakdown region. When the reverse bias on a crystal diode is increased beyond a critical value called the breakdown voltage, the reverse current increases sharply to a high value. The Zener voltage depends upon the amount of doping. A lightly doped diode has a higher breakdown voltage. The main characteristics of Zener diode are: when forward biased, its characteristics are just like those of ordinary diode. A Zener diode is always reverse biased. When reverse biased, a small reverse current flows through it. This current remains constant up to a certain critical voltage called turnover voltage, and then current increases rapidly. The reverse voltage for which the current corresponds to some point on linear portion of reverse characteristic is called the Zener voltage. Did you know? Some materials are classified as semi-insulators. These have electrical conductivity nearer to that of electrical insulators. An example of a common semi-insulator is gallium arsenide. Silicon is the heart of any electronic device. Today, most semiconductor chips and transistors are created with silicon. The electronic areas of a chip are those treated with traces of chemicals such as boron and phosphorus, which alter the conductivity of silicon. Summary. Let us summarize what we have learned. In a semiconductor, valence band filled completely and conduction band is close to it. The conductivity of semiconductor material increases with rise in temperature. Intrinsic semiconductors are those in which impurities are not present and therefore called pure semiconductors. In p-type semiconductor, we introduce trivalent impurity to the crystal structure, such as aluminium, boron or indium. If donor impurities are introduced into one side and acceptor impurities into the other side of a pure crystalline semiconducting material, a p-n junction is formed. A semiconductor diode is basically a p-n junction with metallic contacts provided at the ends for the application of an external voltage. The process of conversion of alternating current into direct current is called rectification, and the circuit for this conversion is called a rectifier. A Zener diode is a reverse-biased, properly doped crystal diode having a sharp breakdown voltage and operated in breakdown region. Introduction. Son, put all the items on the counter table for billing. Yes, Father. Father, I wanna ask you something. Yes, son, you can ask. Father, the shopkeeper using some light device to access the details of all the goods. What is it and how it works? Son, it is a barcode scanner and works on the principle of photodiode. A light source emits the light on the object and reflected light sends by photodiode and produce electrical signals accordingly. It is an application of semiconductor electronics. Okay, Father. I got the answer of my question, and I want to know something more about the semiconductor devices. Students, today we will study more about the semiconductor electronics. Objectives. At the end of this lesson, you will be able to describe optoelectronic junction devices, know photodiode, understand light-emitting diode, describe solar cell, define junction transistor, analyze common emitter transistor, explain transistor as an amplifier, explain transistor as an oscillator. Describe logic gates. Define integrated circuits. Optoelectronic junction devices. The semiconductor diodes in which carriers are generated by photons are called optoelectronic devices. Optical semiconductor devices are widely used in fields ranging from optical fiber communication systems to consumer electronics and have become indispensable devices in the equipment and systems making up the infrastructure of our society. The three important optoelectronic devices are photodiode, light-emitting diode, and solar cell. Photodiode. A photodiode is a receiver for optical signals. It is a reverse biased p-n junction which is designed that light falling on it may enter into the charge depleted region of the junction. When diode is in dark, a small current known as reverse saturation current or leakage current flows in the circuit. This current is due to the drifts of electron-hole pairs which are thermally generated in the charge depleted region. This leakage current increases with the rise in the temperature. The leakage current also increases with the increase in the level of illumination. This is because more intense light would produce more number of electron-hole pairs due to increased number of photons. The photodiode quickly responds to light without any delay. It is used for detection of visible and invisible optical signals. It is used in optical communication, optical switching, and character recognition. Light-emitting diode. It is a semiconducting junction diode which emits light when a current is passed through it in the forward biased condition. It is a p-n junction made of gallium arsenide, GaAs, or some other suitable semiconducting material. The p layer is made thin so that light energy may reach the charge depleted region after traveling a very short distance. When a forward bias is applied to a p-n junction, the barrier height decreases, and with enough forward bias, the charge depleted layer practically disappears. Under forward bias condition, when a current flows through a p-n junction, then several pairs of electron holes recombine and each recombination gives rise to a photon. The frequency of light so emitted depends on the energy released, which in turn depends on the band gap. The intensity of light emitted depends on the number of photons, which in turn depends on the number of recombination taking place. LEDs are available to emit light of all colors. LED requires small voltage and power for their operation. They are used in optical communication devices, TV remotes, and numerical displays in calculators. Solar cell. A solar cell basically converts solar energy into electrical energy. Light energy is made to fall on a metal surface to liberate out electrons from metal, provided the energy of a photon is greater than or equal to the work function of the metal. A p-n junction diode can also give out emission of electrons and holes by absorbing solar energy. The P material at top is very thin compared to thickness of N material. Thus, solar energy photons entering from top glass window easily penetrate up to both sides of junction. As the photons collide with valence electrons of both P and N materials, they impart them sufficient energy so as to leave their parent atoms. Thus, a good number of electron-hole pairs are generated on both sides of junction. Hence, a potential difference is created between anode and cathode. This potential difference can give a current flow through an external load resistance. Junction transistor. A junction transistor is an extended form of junction diode in which there are two junctions between three chips. There are two kinds of transistors are NPN transistor, PNP transistor. NPN transistor. One P material being sandwiched between two N materials. This device is called NPN transistor. PNP transistor. One N material being sandwiched between two P materials. This device is called PNP transistor. The flow of current takes place due to movement of electrons and holes both. Thus, these are called bipolar junction transistors. Components of bipolar junction transistor. Total material is divided into three parts by two junction layers in between are emitter. The first chip of transistor is the emitter, which is heavily doped extrinsic semiconductor. It is heavily doped as it bears the responsibility of supplying the mobile charge carriers to the next chip. Base. This is the middle chip of transistor, which is very lightly doped. The thickness of this part is extremely small compared to the two side chips. Collector. This is the last chip of the transistor which bears the responsibility of collecting the mobile charge carriers coming from base and supply large power to the load. This chip is the thickest one among all three. It is a moderately doped chip. Transistor biasing. In the normal operation of transistor, the majority charges in heavily doped emitter are to be transferred to base region and then from base they have to be transferred to collector region. For transition from emitter to base, the first junction between them has to be forward biased. As the majority charges of emitter reach the base region, they can be attracted towards the collector region only if the collector end is reverse biased. Terminal currents of transistor. We consider PNP transistor to understand about different terminal currents. Emitter current, IE. With forward biasing at the first junction, the majority charges of P emitter move from emitter to base constituting a current called the emitter current. Base current, IB. As the holes reach the base region, most of them are transferred to collector. The small number of holes drifting out from base constitutes a current called base current. Collector current, IC. Most of the holes that go from base to collector form a current called collector current. IE is equal to IB plus IC. The current concepts are all same in PNP and NPN, except the fact that all currents are directed opposite in the two cases. Common emitter transistor input characteristics. In a common emitter configuration, the common or ground side of each voltage source is connected to the emitter. Input characteristics. The variation of base current IB with base emitter voltage VBE at constant collector emitter voltage VCE is called the input characteristic of the transistor. For VCE is equal to 0, the input characteristic is essentially that of a forward biased diode. Increasing VCE with constant VBE effectively means an increase in VCB. This causes a decrease in the effective base width and results in a decreasing recombination base current. For SI transistor, VBE is about 0.7 volt. VCE must be sufficiently larger than 0.7 volt so that the magnitude of the reverse bias voltage VCB across the base collector junction remains high. Input resistance. This is defined as the ratio of charge in base emitter voltage to the resulting change in the base current at constant collector emitter voltage. Common emitter transistor output characteristics. Output characteristics. The variation of collector current IC with collector emitter voltage VCE at constant base current IB is called the output characteristic of the transistor. Saturation region. The part of the characteristic curve lying between origin and the knee of the curve is called the saturation region. In this region, both collector junction and emitter junction are forward biased. Active region. The horizontal part of the characteristic curve is called the active region. In this region, emitter junction is forward biased and collector junction is reverse biased. Cutoff region. In this region, both junctions are reverse biased and the transistor currents are negligibly small. A transistor operating as a switch in the off position is in cutoff mode. Output resistance. This is defined as the ratio of change in collector-emitter voltage to the change in collector current at a constant base current. Current amplification factor. This is defined as the ratio of change in collector current to the change in base current for constant value of collector-emitter voltage VCE when the transistor is in active state. Transistor as an amplifier. Amplification is the process of increasing the strength of a signal. An amplifier is the device that provides amplification without appreciably altering the original signal. We consider the operating point of the transistor somewhere in the middle of this active region. The DC voltage VCE is equal to VCC minus ICRC would also remain constant. The operating values of VCE and IB determine the operating point of the amplifier. If a small sinusoidal voltage is superposed on the DC base, then the base current will have sinusoidal variations superimposed on the value of IB. As a consequence, the collector current also will have sinusoidal variations superimposed on the value of IC, producing in turn corresponding change in the value of V0. VCC is equal to VCE plus ICRL. Nu I is equal to delta IB multiplied by RB plus RI. AC current gain is given by beta AC is equal to IC upon IB. The voltage gain of the amplifier is given by AV is equal to delta VCE upon R delta IB. Or it can be written as AV is equal to minus beta AC RL upon R. The negative sign represents that output voltage is opposite with phase with the input voltage. The power gain of the amplifier is given by AP is equal to product of beta AC and AV. Example. Let's take an example of transistor as an amplifier. The current gain for common emitter amplifier is 52. If the emitter current is 4 milliampere, find the base current and collector current. Let's see the solution. Given values are beta is equal to 52, IE is equal to 5 milliampere. We know that beta is equal to IC upon IB, which is equal to IE minus IB upon IB. On simplifying the expression, we get IB is equal to IE upon 1 plus beta. Now putting the values in the expression and calculating, we get IB is equal to 0.08 milliampere. We know that IC is equal to IE minus IB. Now putting the values in the expression and calculating, we get IC is equal to 3.92 milliampere. Hence the value of base current is 0.08 milliampere and collector current is 3.92 milliampere. Transistor as an oscillator. An amplifier needs an AC input signal to produce an AC output signal. An oscillator converts DC into AC. Most oscillators are amplifiers with the following conditions. A positive feedback to the input must be given from the output. The amplifier gain must be greater than the loss in the feedback path. An oscillator circuit consisting of an amplifier circuit, tuned circuit in the collector and an inductive coupling for feedback. The emitter junction is forward biased while the collector junction is reverse biased. The coils L1 and L2 are wound on the same core so that they are inductively coupled through their mutual inductance. On pressing the key, collector current suddenly starts flowing through L1. Consequently, a voltage is induced with coil L, which charges the capacitor C with such a polarity as to support the forward bias of base emitter circuit. On reaching saturation, collector current stops varying, hence induced EMF in coil L vanishes. The frequency of AC current so produced is given by the relation F is equal to 1 upon 2 pi multiplied by 1 upon under root LC. Logic gates. A signal which varies continuously with time is called an analog signal. A signal which has only two possible discrete values is called a digital signal. Such signals are conveniently represented by binary numbers which has only two digits, 0 and 1. Logic gates are digital circuits that follows certain logical relationships between the input and output voltages. The basic logic gates are OR, AND, NOT, NAND, NOR. Truth table. A table that shows all possible input combinations and the corresponding outputs for a logic gate is called truth table. Boolean expression. A shorthand method to describe the functioning of a logic gate in the form of an expression is known as Boolean expression. OR gate. An OR gate has two or more inputs with one output. The output Y is 1 when either input A or input B or both are 1. That is, if any of the input is high, the output is high. AND gate. An AND gate has two or more inputs and one output. The output Y of AND gate is 1 only when input A and input B are both 1. NOT gate. This is the most basic gate, with one input and one output. It produces a 1 output if the input is 0 and 0 output if the input is 1. That is, it produces an inverted version of the input at its output. It is also known as an inverter. NAND gate. This is an AND gate followed by a NOT gate. If inputs A and B are both 1, the output Y is not 1. NAND gates are also called universal gates because using these gates we can realize other basic gates like OR, AND, and NOT. NOR gate. It has 2 or more inputs and 1 output. A NOT operation applied after OR gate gives a NOT OR gate. Its output Y is 1 only when both inputs A and B are 0. Integrated circuits. An integrated circuit is a small electronic device made out of a semiconductor material. The first integrated circuit was developed in 1950s by Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor. Integrated circuits are used for a variety of devices, including microprocessors, audio and video equipment, and automobiles. Integrated circuits are often classified by the number of transistors and other electronic components they contain. SSI, Small Scale Integration, up to 100 electronic components per chip. MSI, Medium Scale Integration, from 100 to 3000 electronic components per chip. LSI, Large-scale integration, from 3000 to 1 lakh electronic components per chip. VLSI, Very large-scale integration, from 1 lakh to 10 lakh electronic components per chip. ULSI, Ultra-large-scale integration, more than 1 million electronic components per chip. Did you know? LEDs are instant on, which means they achieve their optimal brightness immediately upon being powered on. The largest solar electric plants are located in Germany. They are the Bavaria Solar Park and the Arnstein Solar Electric Plant. The Arnstein plant delivers 12 megawatt of energy to about 3,500 households. Transistors have shrunk in size with a factor of 222 since the first Intel 4004 chip was introduced in 1971. Summary. Let us summarize what we have learned. The semiconductor diodes in which carriers are generated by photons are called optoelectronic devices. A photodiode is a receiver for optical signals. LED is a semiconducting junction diode which emits light when a current is passed through it in the forward biased condition. A solar cell basically converts solar energy into electrical energy. In a bipolar junction transistor, the flow of current takes place due to movement of electrons and holes both. Emitter is the first chip of transistor, which is heavily doped extrinsic semiconductor. Most of the holes that go from base to collector form a current called collector current. Logic gates are digital circuits that follow certain logical relationships between the input and output voltages. An integrated circuit is a small electronic device made out of a semiconductor material.
तो मेरे प्यारे दोस्तों, ये था सेमीकंडक्टर इलेक्ट्रॉनिक्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट।
Yeah!